Hello, everyone, and welcome to this new series on earthquakes and seismology. As the first disclaimer, of course, the content of this presentation is mainly informative and should not in any way or form be used as a replacement of the official scientific documents or guidelines on earthquakes and any other subject, actually. Starting from Module 1, Introduction to Earthquake Science. Okay, what is an earthquake? What's the definition? An earthquake is the sudden release of stored elastic energy within the Earth's lithosphere, which is the crust and the mantle, the two layers above the core of the Earth, resulting from rupture along geological faults. These are like the seizures or like the incisions, the scars around the globe, okay, which are called fault lines because they are weak points that are often affected by earthquakes. Why? Because they have moving tectonic plates underneath them. Okay, so from rupture along geological faults or rapid deformation of rocks. So again, an earthquake is the sudden release of stored elastic energy within the Earth's lithosphere, resulting from rupture along geological faults or rapid deformation of rocks. This released energy propagates through the Earth in the form of seismic waves producing ground shaking and surface displacement. Earthquakes occur primarily due to tectonic stress accumulation caused by the motion of lithospheric plates. So they push and pull against each other, and rocks deform elastically until the applied stress exceeds their mechanical strength. This is when a breaking occurs, or a brittle failure and a fault slip. What do we mean by that? An elastic deformation means that, let's say you have a spring or a metal. Once you release the pressure, it retains or restores its original form, its original shape. Okay? A plastic deformation is when the pressure exceeds that, goes beyond that. And once you release that pressure, the new shape that has been taken by the spring or the metal, okay, is permanent. Like the metal or the rock in this case can no longer restore its original shape, its original bending. Because why? Because it has been deformed beyond limit. So it breaks. In the case of rocks, they break. Okay? They don't simply plastically deform, they break, and that brittle failure causes an earthquake. Okay? So it leads to a brittle failure and fault slip. Stress and strain, the elastic behavior of rocks prior to rupture follows Hooke's law. Sigma is equal to E times epsilon. This is the law. Sigma is the stress in Pascal, E is the Young's modulus in Pascal, and epsilon is the strain, which is a dimensionless value. Okay, E, which is Young's modulus, is a material property that measures stiffness by defining tensile, okay, and compressive stress. Tensile meaning you're stretching something, compressive, you are pushing, you're pressing against something. So by defining tensile, compressive stress, and axial strain, which represents how easily a material stretches or deforms. So this is Young's modulus that changes from one type of material to another. Okay, stress accumulation stores elastic potential energy, correct? When failure occurs, that energy is released as seismic energy. To give a simplified example, let's say you have a plate of metal, okay, let's say iron or something like aluminium, okay, and it has some thickness, but it can be bent, let's say, all right? Anything has some degree of elasticity, by the way. So let's say you bent it, okay? Now you have two choices. Either you release it like this and it goes back to its original form. So it's elastic energy, which is a form of potential energy, has like restored its original shape when you you've released that potential energy, so it came back, by the way, with a velocity. So it kind of turned into a kinetic energy, restoring the original shape of the plate of aluminum. But let's say you keep pushing and it breaks, but somehow, like one way or another, this potential energy, this elastic energy needs to be released. So in such case, when you break the metal, when you keep pressing until you have indefinitely deformed, like it can no longer go back to its original form, so it had lost its elasticity, then it will break, and that breaking, that rupture will be released in a form of seismic energy in such case, okay, in the form of vibration. So one way or another, that energy would be released. In such case, it will release seismic energy causing waves, okay. That would be the result of that breaking within the earth, causing earthquakes and seismic activity. Elastic rebound theory, proposed after the 1906 San Francisco earthquake. The elastic rebound model explains earthquakes as a cycle of stress accumulation, 1, elastic deformation, 3, sudden rupture, 4, energy release and rebound, where m0 is equal to the seismic moment in Newton per meter. U is the shear modulus of rocks in Pascal. By the way, the shear modulus is actually the tendency of a material or a substance or a metal to be deformed. Okay. A is the rupture area in meter square, and D is the average fall displacement M. Okay. So you have stress accumulation. The earthquakes are a cycle of stress accumulation, elastic deformation, sudden rupture, suddenly something breaks, okay, and energy release and rebound. The energy is released and rebounds around different rocks, different formations of the earth. The seismic moment, which quantifies earthquake size, is defined as m0 is equal to mu AD. So the seismic moment is given by mu, which is the shear modulus of rocks, their tendency to be deformed, multiplied by the area of rupture, multiplied by D, which is the average displacement in meter, average displacement of Earth in meters. Now let's tell the story in a sequential manner. You have at first stress accumulation due to tectonic plates moving against each other and pressing against each other, which leads to an elastic deformation. Elastic deformation means that the plates up to that point, they are deforming. Elastically means that, let's say, supposedly, if the pressure was to be released, these plates can restore or retain their original shape, okay? Like a spring. When you release a spring, you have up to a specific point, a certain point, you can still release the spring, and it will go back to its original coiling, its original shape, and its original size. This is what we mean by elastic deformation. But you get to a point beyond that, beyond what the spring can hold, the stress that it can withstand, so to speak, and here in our case, the rock, you get a sudden rupture, meaning that it can no longer hold the stress. Okay, the potential energy has exceeded its limit, the elastic energy. So it ruptures, it breaks, and that rupture would release energy, waves, okay, seismic waves, and these waves would rebound, and this is what will cause earthquakes, okay? And then the rebound, which means that the wave will travel within the earth and get back another time, okay? And rebound in another places even. Historical development of seismology. Seismology is the scientific study of earthquakes and seismic wave propagation. Early observations. Ancient civilizations documented earthquake effects, but scientific understanding began with instrumental measurement. Key milestones include first seismoscope invented in China, 132 CE, which is after Christ, actually, okay, not common era. Development of mechanical seismographs in the 19th century. Recognition of elastic rebound theory in the early 20th century. Okay, so yeah, these different stages are the ones that we went through in developing earthquake theories. Modern seismology, advances in physics and instrumentation, enabled quantitative analysis of seismic waves. Wave propagation is governed by the elastic wave equation, which is here nabla u square, or the second gradient of u is given by 1 divided by v square, which is the seismic wave velocity, multiplied by the displacement of the earth. Okay, this is the second derivative of displacement, which means the acceleration of displacement. Okay, because the first derivative of u being displacement field would give us the speed of displacement. That's the first derivative. The second derivative would give us the acceleration or the concavity, okay, which is the velocity of the speed, like the acceleration of displacement. That's the speed of displacement, so to speak, and divided by t. Like, it's not divided by t, but it is the displacement acceleration in terms of time. This is what gives us the overall wave, like the overall displacement field. Seismic velocities depend on material properties. Now, you have two types of waves. We have the P wave and the S wave. The P wave is longitudinal. It is a compressional wave that travels much faster than the S wave, and it travels through rocks, through sand, through soil, through metals, and through liquids, even gases. Okay? Meanwhile, the S wave is not longitudinal, it is perpendicular. Okay? It is normal to the soil. So it's a shearing wave. It goes like this, it shakes the earth. Okay? But the other wave, the P wave, goes longitudinally throughout the surface of the earth. Now, Vp and Vs. Okay, Vp is given by the square root of k plus 4 divided by 3 mu divided by rho. K is the bulk modulus, which is the argument that defines the resistance against compression. This is K. Okay? Mu is the shear modulus, which defines the rigidity or resistance to deformation when subjected to tangential force or shear stress. And rho is the density of the soil. So Vp is given by square root of k plus 4 divided by 3 mu divided by rho. That's the P wave velocity. The S wave velocity is given by square root of mu divided by rho. Mu is the shear modulus and rho is the density. Here in this illustration, we see different types of waves. So we've spoken about the P waves that are compressive longitudinal waves. You see here compressions and expansions. The S wave, which is a shear wave, 90 degree, vibrating 90 degree against the soil or the earth, okay? And it doesn't travel through gas and liquid, unlike the P wave, which travels through rocks, gas, and liquids. You have the love wave that travels sideways, and the Rayleigh wave, which are rotational waves. Here in this illustration, we see the hypocenter, which would be the source of the earthquake, or where the break took place within the earth. Then the epicenter is the location above that on top of the earth. Okay, so it would be the geolocation on the crust, okay, above the hypocenter. And the focal length is the distance between the two. This would be the fault plane, okay, the plane of the fault meaning the direction of the breaking. Epicentral distance would be the distance from the seismic center, okay, seismic measurement center, and the epicenter, which is the point above the earth where, you know, above the hypocenter, where the earthquake had taken place. Now here is how we measure the magnitude of an earthquake based on the Richter scale. So you have the distance to epicenter in kilometers. You get that, let's say the distance is, for instance, 200, okay? 200 kilometers. And let's say the amplitude on the seismogram in millimeters, and this is the seismogram. Let's say the amplitude here is 50 millimeters, okay? That is 50 millimeters, the highest peak. So you go here and you check 50, and then you relay these two lines, these 2 points by a line, okay? So it crosses at 5. So the Richter magnitude of this earthquake would be 5 degrees, which is pretty severe, by the way. Importance of earthquake studies. Earthquake science plays a critical role in reducing societal risk and improving infrastructure resilience. Scientific importance: understanding Earth's internal structure through the earthquakes, because due to the fact that different waves travel in different materials, studying plate tectonics and also have different damping or amplitude reduction rates as they travel in different types of rocks, studying plate tectonics, and monitoring crustal deformation. Engineering importance: ground motion determines structural response. Newton's second law governs building dynamics, is given by F is equal to ma. During earthquakes, inertial forces acting on structures are Fs is equal to the mass, the structural mass, multiplied by A, which is the ground acceleration in such case. So Fs would be the seismic force, is equal to m, structural mass, multiplied by the Ag, or ground acceleration. Understanding these forces enables earthquake-resistant design. Global earthquake distribution. Earthquakes are not randomly distributed but concentrated along tectonic plate boundaries. Major seismic belts include Circum-Pacific Belt or Ring of Fire, that goes, by the way, also around the shores of Australia. It's very major ring that's highly active, okay? Not active today, but that's highly prone, like active under the ground, okay? And even it has volcanic ruptures. Alpine Himalayan belt, mid-ocean ridge systems. Plate motion velocity contributes to strain accumulation. So the plate motion velocity, it contributes, it adds to strain accumulation. So the strain rate is given by V, which is the relative plate velocity, divided by L, or the characteristic deformation length. Regions with higher strain rates generally experience higher seismic activity. The Gutenberg-Richter frequency magnitude relation describes earthquake occurrence statistically. So it's like a probabilistic measurement. Log base 10 of n, which is the number of earthquakes, is given by A minus B times M. M is the magnitude of the earthquake, and A and B are empirical constants. Overview of seismic hazards and risks. Seismic hazards refers to the probability of earthquake-induced ground motion, while risk includes potential consequences to society. The primary hazards: ground shaking, surface rupture, of course, that could be the consequence of the earthquake, and fault displacement, meaning that the fault had moved, like the incision or like the scar on the earth would move, would be displaced, would either grow larger, wider, or it would be displaced from one point to another. Secondary hazards would be ground liquefaction, so the soil would be more broken, landslides, okay, tsunamis, when you have a landslide within the seabed, okay, it would cause a wave, a ripple wave that would get to shore and cause tsunamis, and infrastructure failure, which means the breaking or the collapse of buildings and different other infrastructures. Ground motion parameters, peak ground acceleration PGA is commonly used. PGA is given by max of second derivative u divided by dt squared. Seismic risk can be conceptually expressed as risk is equal to hazard multiplied by the exposure multiplied by vulnerability. Let's break them down. So the risk is equal to the product of these three. So they amplify each other. The hazard is equal to the probability of shaking. Exposure is the population and assets that are existing in a location, and vulnerability is equal to the susceptibility to damage, which means how weak are the buildings, how modern or ancient is the infrastructure, etc. So the peak ground acceleration, again, going back to this one, to this formula, is given by the maximum value, okay, for the second derivative of the displacement, which means the acceleration, by the way. The second derivative is actually the velocity or the speed of the change of a velocity, the rate of change of a velocity in terms of time. In other words, the acceleration. Okay, so it is the concavity on a curve. Again, the peak ground acceleration PGA is equal to the maximum value of the acceleration of displacement in terms of time, displacement of the ground. Finally, earthquake science integrates geology, physics, engineering, and risk analysis to understand how tectonic stresses generate seismic activity or seismic waves and how these events impact society. The foundational principles introduced in this module provide the basis for advanced study of seismic wave propagation, earthquake measurement, and hazard mitigation. Module 2, Structure of the Earth. Overview. Understanding the internal structure of the Earth is fundamental to earthquake science because seismic activity originates from mechanical processes occurring within the planet's outer layers. Okay, the crust and below the crust. Knowledge of Earth's composition, mechanical behavior, and thermodynamics explains plate motion, stress accumulation, the tectonic plate motion, accumulation of stress when they push against each other due to the motion itself, and earthquake generation. Earth structure is inferred primarily from seismic wave propagation, gravity measurements, laboratory rock physics, and geophysical modeling. This is how actually we've discovered the structure of the Earth, by measuring the seismic activity itself. Because as the wave travels through different layers, through different materials, the characteristics of the wave would determine what kind of layer you're going through, whether metallic, whether rocky, silicate, soil, because the frequency and the amplitude would change as the wave goes through different substance, different material, different structure. Internal layers of the Earth: crust, mantle, and core. The Earth is divided into three major compositional layers based on chemical composition and seismic properties. Okay, here if we look at this illustration, you have the inner core and outer core, but both of them make up the core. So 1400 miles thick, the outer core, made of iron and nickel in liquid state. Okay, the inner core is solid, which is 800 miles. The mantle is around 1000 miles thick. Okay, flows with the consistency of asphalt, and you have the crest, which is the outer layer, 3 to 5 miles thick. Okay, and 5 to 25 miles thick in some areas. So the crust is the outermost solid layer, thickness 5 to 10 kilometers oceanic and 30 to 70 kilometers continental. Here we're talking about we're talking about the thickness of the crest, and in terms of kilometers, that's the difference. Okay, here it's expressed in miles. So 5 to 10 kilometer oceanic, 30 to 70 continental. Composition: silicate rocks and density is around 2,700 to 3,000 kilogram per meter cubed. Seismic wave velocities, which is the P waves here we're talking about, increase with depth due to increasing pressure and rigidity. Okay, so Vp is equal again to square root of K, which is the bulk modulus plus 4 divided by 3 mu divided by rho. So Vp, which is the compressional wave velocity, K is the bulk modulus, which is the modulus that defines the rigidity of solid, shear modulus, the resistance against deformation, that's the shear modulus, and rho is the density. Now, as you go deeper within the Earth, what increases is both K and mu, which is the bulk modulus, respectively, and the shear modulus. Bulk modulus, of course, being how rigid the solid or the material is, okay? And mu is the resistance against deformation. So due to a much higher pressure, okay, and due to the fact that the rocks would be more under pressure, okay, with the increase of pressure, you would have more rigidity. So the velocity of the waves, which are the P waves in such case, compression waves would increase due to this fact. Now, in contrast, near the surface of the Earth, the waves would be traveling much slower due to the fact that the bulk modulus is less. You have a soil material with less rigidity, with less shear modulus, so you would have a more of a damping effect, okay, a deceleration effect for the seismic waves. Second, the mantle. The mantle extends to a depth of approximately 2,900 kilometers and constitutes about 84% of Earth's volume. Composition: ultramafic silicate rock or periodite. Behavior is solid but capable of slow viscous flow, so it's kind of liquefied. The pressure increases with depth according to hydrostatic equilibrium. So dP, or the differential of pressure over R, okay, over the distance that's being traveled downward, okay, or the thickness of soil, so to speak, above the object where you are measuring the pressure, is given by minus rho g. Okay, P is the pressure, R is the radial distance, and G is the gravitational acceleration. The mantle convection drives plate tectonics and earthquake producing stresses. So the convection of the mantle, convection means the transfer of heat energy, drives plate tectonics and earthquake producing stresses. It is what causes them. So to give you an example in physics, let's say we're talking about a body of water. So what would be the pressure at, not the bottom, but let's say this is the bottom here, and this is an object at a depth h from the surface of the water. The pressure would be given by P is equal to rho g h. H is this distance, G is the gravitational acceleration, and rho is the density of water, which is, by the way, 1,000 kilograms per meter cubed. 3. The core. The core consists primarily of iron and nickel and is divided into the outer core, which is a liquid structure, about 2,900 to 5,150 kilometer depth. Inner core, solid state, 5,150, 6,371 kilometer in depth. The S waves cannot propagate through liquids, as we mentioned before. So the velocity of the S wave is given by square root of mu divided by rho. Okay? Since mu in liquid is 0, which is like the shear modulus again, which is the resistance of a material against deformation. Liquids have no resistance against deformation. They can easily be deformed. That's why Vs is equal to 0, and hence the velocity of an S wave would be 0. So in other words, it would be stopped by a liquid body, confirming the liquid nature of the outer core. So an S wave cannot travel in liquids or gases or in fluids in general. Lithosphere and asthenosphere. Earth's outer region is also classified mechanically. You have the lithosphere, which includes the crust, the external layer, the covering layer of the Earth, the uppermost mantle, or like the part of the mantle that is the closest to the crust. Its characteristics are it's rigid and brittle, thickness around 50 to 200 kilometers, and it's broken into tectonic plates. Earthquakes primarily occur within the lithosphere. Asthenosphere, located beneath the lithosphere, the asthenosphere is weak and ductile, so it's not rigid, partially molten due to magma, due to a high temperature, so it's mainly magma and lava, capable of slow flow, so it's flowing slowly, it has some kind of viscosity. Viscous deformation follows Newtonian creep, which is given by sigma is equal to eta epsilon, where eta is the viscosity and epsilon is the strain rate. This layer allows tectonic plates to move due to its liquid structure and due to the convection that we've spoken about, which is the heat transfer from the bottom of the Earth to the top layers. Plate boundaries and tectonic settings. Earth's lithosphere is divided into moving tectonic plates interacting at boundaries where earthquakes are concentrated. Okay? You have the divergent boundaries. Plates move apart. Okay, epsilon, which is the strain rate, is given by V divided by L. V is the spreading velocity and L is the deformation length. Earthquakes are typically shallow. They are not so deep and moderate, okay, to a certain extent. Convergent boundaries. Plates collide. This is what builds up stress, by the way, producing subduction zones and powerful earthquakes. Stress accumulation relates to shear stress, okay, which is a lateral stress, a sideways stress. Stress accumulation relates to shear stress given by mu gamma, okay, that's the shear stress, and gamma is the shear strain, okay? Mu is the shear modulus again. These zones generate the largest megathrust earthquakes. Transform boundaries. Plates slide laterally past each other. So they don't collide, they slide laterally past each other. Fault motion produces strike-slip earthquakes governed by frictional resistance. So the stress is given by mu F times sigma n, where Cf is the frictional, or tau F is the frictional shear stress, Uf is the coefficient of friction, and sigma n is the normal stress, which is the stress applied normally to the plate. Mechanical versus chemical layering. Earth can be classified into two different frameworks. 251, chemical compositional layers, which are made by crust, mantle, core, defined by mineral composition, and mechanical or rheological layers. So you have the lithosphere is characterized as a rigid layer or a rigid area, which is made by the crest and the upper most part of the mantle. Asthenosphere, which is the lower mantle with the core, is ductile. Mesosphere, it is strong. Okay, that's the lower mantle. Outer core is liquid, made of iron and nickel, and inner core is solid. It has a solid state. Mechanical properties control earthquake behavior and seismic wave propagation. Elastic response follows. Sigma Ig is given by CIGKL, epsilon KL. This represents the elastic stiffness constants, CIJKL. Heat transfer inside Earth. Earth's internal heat drives mantle convection, which is the heat transmission through the mantle, or heat transfer. And plate tectonics also are pushed by that heat. Primary heat sources are radioactive decay from within the core and the liquid core, basically from primordial heat, due to high pressure, by the way, all of that. Core crystallization of the inner core, and heat transfer occurs through the following. Conduction, governed by Fourier's law. It's given by, Q equal minus K nabla T. Q is the heat flux, K is thermal conductivity, and nabla T is the temperature gradient or variation of temperature. By the way, the thermal conductivity has to do with the material that's conducting or transferring the heat, like whether it was metal, rock, etc. Convection, mental convection transports heat through fluid-like motion. This is given by the Rayleigh number, Ra equal rho g alpha delta T d to the power of 3 divided by K eta. So, rho is the density, of course, g is the gravitational acceleration, alpha is the thermal expansion coefficient multiplied by the delta T, which is the differential of temperature or temperature difference times d to the power of 3, which is the layer thickness, the convection layer thickness, divided by K eta. K is the thermal diffusivity here, and which is kappa, by the way, and eta is the viscosity of the fluid or the material. Convection occurs when Ra exceeds a critical value. Finally, the structure of the Earth combines compositional layering, mechanical behavior, and thermodynamics. The rigid lithosphere moves over the ductile asthenosphere due to mental convection or the fluid-like transfer of heat from the core all the way to the upper mantle and crust, which is the lithosphere. This is driven by internal heat, due to high pressure. Plate interactions that are, by the way, being moved due to convection and heat transfer because of the fluid motion. It's like you have a current, an undercurrent, driven by the differential of temperature that is moving the plates under flow of, the viscous internal of the Earth. So the plate interactions generate stresses that ultimately produce earthquakes due to breaking or gritting when they slide one tectonic plate above the other, making Earth's internal structure central to earthquake science. Module 3, Plate Tectonics. Introduction. Plate tectonics is the unifying theory explaining large-scale geological processes on Earth, including earthquakes, volcanism, and mountain formation. The Earth's lithosphere is divided into rigid plates that move relative to one another over the ductile asthenosphere, which is more liquid. Interactions at plate boundaries generate stresses that ultimately produce earthquakes. By the way, let's say two tectonic plates are pushing against each other, so the surmountable pressure would go above and it would be pushing the crust, creating mountains. This is how mountains forms. And on the other hand, or contrary to that, a slip in the plates, plates slipping one beneath the other, when the subductile formation would form things like rivers, like valleys, when a plate is going beneath the other plate. It's pushing it like this. Theory of plate tectonics. The theory of plate tectonics combines earlier concepts of continental drift and seafloor spreading into a single framework describing lithospheric motion. Key principles include the lithosphere is fragmented into tectonic plates. Plates move at rates of a few centimeters per year. Plate interactions occur at boundaries where two plates meet, and this is where most earthquakes occur. These are like the faults, the locations of the faults. Plate motion can be described kinematically by velocity vectors. So relative velocity is given by v1, which is the speed of one plate, minus v2, the speed of the other plate, two adjacent plates. and this would be the relative velocity of both. Accumulated deformation produces strain. This is given by epsilon is equal to delta L, which is the differential of length, okay, divided by the length before the strain had occurred, before the deformation or not like the shearing occurred. And stress developed according to elastic behavior, which is sigma is equal to E, or Young's modulus, multiplied by the strain, which is epsilon. Of course, sigma being the stress. Again, the strain is the displacement in relation to the original length. So it is the displacement, or delta L, which is L2 minus L1. So the new length after the strain minus the original length divided by the length, or the length displacement ratio. Okay, so it's like the percentage of displacement, how much of length has changed in reference to the original length of a scar or a fault. Types of plate boundaries. Plate boundaries are classified according to relative motion. You have first divergent boundaries. At divergent boundaries, plates move apart and new lithosphere forms through mantle upwelling. Okay? Characteristics: mid-ocean ridges, correct? Shallow earthquakes and volcanic activity. The spreading rate is given by R equal D divided by T. D is the distance between magnetic stripes and T is the age difference. Extensional stress dominates, so sigma T is given by F divided by A, force divided by the area where the stress is applied, where F is tensile force and A is area. To explain further how the upwelling occurs and how the divergent boundary or divergent boundary mechanics work, this is an illustration here. You see, as these two tectonic plates move away or further from each other, what happens is that the lithosphere, which is the upper crust with the crust with the uppermost part of the mantle, becomes thinner and thinner. So this renders this entire layer, if we would consider it as a hybrid layer made of the crust and the uppermost mantle, this layer becomes thinner and less strong, so it becomes more vulnerable against the upper pressure coming from the mantle, okay, coming from the asthenosphere. So the pressure of the mantle against the crest, which becomes of a stronger effect, is now able to push against and deform the upper layer, the upper crust. Since the earth over there, the rigid earth made by the crust and the lithosphere in general, has thinned right now. It became weaker, more vulnerable due to the moving motion, due to the divergent boundary. So the upwelling motion of the magma, it pushes through, okay, it can form volcanoes, volcanic activities, and more than that, it creates ridges such as the ones that you see at the bottom of the ocean. On the other hand, you have convergent boundaries. Convergent boundaries occur where plates collide instead of going apart from each other. One plate may subduct beneath another, like the one you're seeing here. It's subducting beneath this other plate, forming deep trenches and powerful earthquakes. Types include oceanic continental convergence, oceanic convergence within the ocean, and continental collision. And this, by the way, would form volcanoes, would form also trenches. Subduction generates compressional stress given by sigma C is equal to minus F divided by A, where F is the tensile force divided by A, or area of exposure, area to which this tensile force is being applied between the two plates, of course. Earthquake magnitude relates to seismic moment given by m0 is equal to mu AD, where mu is the shear modulus or the resistance of a material against deformation. A is the rupture area multiplied by D or the average displacement. So this is the average displacement of matter. These regions produce the largest megathrust earthquakes. Transform faults, the third type. Transform boundaries involve lateral sliding between plates. Characteristics: you have the strike-slip motion, shallow focus earthquakes, okay, they are shallow, basically, high shear stress accumulation, and frictional resistance along faults follows. T, which is the stress, is given by mu F sigma n. Okay, shear stress is given by coefficient of friction, mu F, multiplied by the normal stress, 90 degree to the plate, basically. Stick slip motion along transform faults produces sudden seismic rupture. In this illustration, this is how actually the transform faults or transform boundary works. So you have two pieces of land, two tectonic plates, so to speak, not pieces of land, shearing against each other like they are crossing next to each other. Okay, it is a strike slip motion, and you have shallow focus earthquakes again. Okay, and you have high shear stress accumulation due to the gritting motion, due to that friction. And it's a frictional resistance that follows this formula that we've just spoken about. Plate motion mechanics. Plate motion is driven by forces arising from Earth's internal heat and gravity. Mantle convection, which is the fluid-like flow of heat or heat transfer that is fluid-like from the mantle, actually the liquid core, through the mantle all the way to the lithosphere. Mantle convection, thermal convection transfers heat through the mantle. Convective vigor is measured by the Rayleigh number. Ra is given by rho g alpha delta t d to the power of 3 kappa eta, where rho is the density of the mantle in such case, g is the gravitational acceleration, 9.8 meter per second square, alpha or thermal expansion coefficient, delta t, which is the temperature differential, times d to the power of 3, which is in such case the mantle thickness, divided by kappa, thermal diffusivity, times eta or the viscosity of the mantle liquid or substance. Convection occurs when Ra exceeds a critical threshold. Ridge push. Elevated mid-ocean ridges create gravitational sliding forces given by FRG is equal to rho, FRP rather, is approximately proportional to rho GH. Rho GH, by the way, being the pressure. So this is the ridge elevation multiplied by G, and the density, this is the pressure actually. Now, the slab pole, dense subducting plates sink into the mantle. These would be the plates that are pushing against another horizontal plate, but as they push, they are sinking deeper within the mantle, and they generate a pulling force. FSP is given by delta rho, which is the differential of density multiplied by G, or the gravitational acceleration, times V, which is the slab volume. Slab pole is considered the dominant driving force of plate motion. Now, as a side note, if you notice that rho GH is actually, again, the formula for the pressure, okay? The hydrostatic pressure. So when we are measuring the pressure against an object located at the bottom of a lake, the pressure would be rho GH, with rho is the density of water, G is the acceleration, gravitational acceleration of gravity, and H is the height of the water above that object. So the ridge push has to do with the pressure. Okay? But on the other side, the slab pull is the exact opposite. Slab pull is actually the buoyancy that pushes upward, not downward. The pressure pushes downward and also sideways, but the pull pushes upward, this is caused by the buoyancy of the fluid-like substance, okay? So the pull is given by FSP is equal to, that's the force of the pull. The force of buoyancy is given by the differential of density times G, which is the gravitational acceleration, times volume, which is the slab volume. Now, as a reminder, this is the formula for buoyancy. The force of buoyancy is given by rho Vg, with V being the volume of the submerged object, okay? So the volume, let's say this is the plate here, okay? So how much of that plate is being submerged by the mantle? Let's say this is the area where this plate is submerged in the mantle, okay? So the area, how much thickness is there to that area? Let's say the thickness would be a kilometer, okay? And the area here, let's say 2 kilometers by 0.5. So what would be the volume? The volume of the part of the slab that is submerged, okay? In other words, it is the volume of the fluid or the magma or the mantle that has been displaced when the slab went into the mantle. The volume would be 0.5 times 2 kilometers times 1. So around 1 kilometers cubed, okay? Of course, you need to then use the metric scale. Rho is the density of the magma. I'm sorry, this is rho. And G is the acceleration of gravity, 9.805 approximately, or 85, approximately that. And you get the force. That would be the force of pulling, which is, again, it is the same force of buoyancy in classical physics. Actually, this is part of classical physics, but it is applied to tectonic plates here. Continental drift and seafloor spreading. Continental drift, originally proposed by Alfred Wegener. Continental drift suggests continents were once joined in a supercontinent, Pangaea, and later separated. By the way, this is how you notice it. Because if you look at the globe, you see that America can perfectly fit, like Northern and Southern America, can fit like a puzzle with Europe, with the African continent. It's like they used to be one plate and then they had separated. Okay, evidence includes fossil correlation between different parts of these continents at the edge shores, matching coastlines, which means that they can match together as different pieces of the same puzzle, and paleoclimate indicators also. Now, the paleoclimate indicators have to do with matching patterns of climates between different pieces that used to be together. Okay, this is as a broad term. Seafloor spreading. New oceanic crust forms at mid-ocean ridges and moves outward. This can give you the velocity of the plate itself. How do we measure it? Because magnetic striping records or records geomagnetic reversals. So you have the plate velocity is calculated by x, which is the distance from the ridge, distance of displacement from the ridge, as these two parts of the ridge keep on traveling outward as the plate keeps moving far away from the ridge center, divided by t, which is the crustal age that can actually be measured in 1, 2, 3, 4 years, let's say. How far did the plate travel away from the ridge, okay? Or let's say, how far did the ridge move outwardly from its center? So V is equal to x divided by t, which is displacement or distance from the ridge, divided by t, which is the period of time of measurement. It would give you the velocity of movement of the plate. Earthquake generation zones. Earthquakes occur when stress accumulates faster than it is released. Exactly. So it keeps on accumulating, and at a certain point, the rock or the plate loses its elasticity. It can no longer bend, so it breaks, releasing an enormous amount of energy in the form of seismic waves. Elastic strain energy, stored elastic energy per unit volume, is given by U is equal to 1/2 sigma epsilon. Energy released during rupture produces seismic waves. Here, by the way, sigma is the stress being applied and epsilon is the strain. 1/2 of the product would give you the stored elastic energy per unit volume. Depth classification, you have shallow earthquakes, less than 70 kilometers, intermediate earthquakes between 70 and 300 kilometers, so they occur much deeper, and deep earthquakes at a depth of 300, 700 kilometers. Subduction zones form inclined seismic regions known as Wadati-Benioff zones. Okay. So what does it mean to have an inclined seismic region? Let's say you have the subduction zones like that, and the break happens in this way here. Okay. So the seismic region would be inclined. It wouldn't be parallel to the horizon. So the wave would travel in a way like that. Not as you assume traveling outward like a normal to the surface of the ground. It would be traveling sideways. Okay? Having a different direction, different heading. So the affected regions would be different. Finally, plate tectonics explains the motion of Earth's lithospheric plates and provides the physical framework for earthquakes generation. Divergent, convergent, and transform boundaries produce distinct stress regimes and seismic characteristics. So they have different fingerprints, okay, different signatures. Plate motion driven by mantle convection and gravitational forces, also gravity plays a role, leads to strain accumulation, fault rupture, breaking of a plate, a tectonic plate, or its side, so to speak, and seismic energy release, making plate tectonics central to earthquake science. Module 4, Stress, Strain, and Rock Mechanics. Introduction. Earthquakes originate from the accumulation and sudden release of mechanical stress within rocks of the Earth's lithosphere. Rock mechanics studies how geological materials respond to applied forces through deformation, elastic or plastic deformation. Elastic means it can retain or restore its original shape, but plasticity means that once something gets to a point, it can no longer recoil and retain and restore its original shape or form. It loses its resilience, correct? Failure and faulting. Understanding stress and strain relationships is essential for explaining earthquake initiation and fault behavior. Types of geological stress. Stress is defined as force applied per unit area, given by sigma is equal to F divided by A, where F is the applied force in Newton and A is the area in meter square. Stress is given in Pascal. Now, stress in the Earth is generally represented by a tensor or a multi-dimension vector, okay, two-dimensional vector, describing forces acting in multiple directions, actually three-dimensional, X, Y, Z. So sigma Ig or Ij is given by sigma Xx, tau Xy. So you have tensile and shear stress depending on the direction. This is why you have two different stress symbols. Where normal stress is sigma, okay, it acts perpendicular to surfaces, okay. That would be the tensile stress of pulling or pushing, okay, pulling. Meanwhile, the shear stress, tau, act parallel. So to give you a visualization on how it works. So let's say this is, okay, a part of a land. So the tensile stress would be pushing outward. That would be the tensile stress. So it would be longitudinal to this Earth cube, so to speak, this section of the Earth. Meanwhile, the shearing stress, it would be pushing sideways. That would be the shearing stress. It is like, give you an example. Let's say you have a set of books mounted on top of each other. The shear stress would have the tendency of pushing the books, or like a set of papers. It would be pushing the papers sideways. So they would be displaced like that. So one paper would go further than the ones on the bottom. So the one that would go further is the one that has the force applied directly to it, and others would start displacing, but the one at the bottom would stay in its location without displacement. Meanwhile, that would be the shear stress. Tensile stress is like when you pull against a spring, correct? So that pulling motion is a tensile stress longitudinal with the direction of the spring. Okay, of course, in such case, it will cause an elastic motion, an elastic expansion of the spring itself. Compressional stress. Compressional stress occurs when forces push rocks toward each other. That would be the exact opposite of tensile stress. It would be compressional, so it would be pushing rocks against each other, shortening and thickening the material. Okay, it would increase the density of the material, by the way, and it would make it thinner by increasing its density while reducing its thickness. Okay, so it has a compressive effect. So sigma c less than 0. Effects include folding, reverse and thrust faulting, mountain building. So it can create a mountain due to the pressure applied between two tectonic plates. So it would be pushing the soil against each other, thickening, like increasing the density, but that surmounting pressure needs to be released in one direction or the other. So it would be pushing along with the mantle pressure, the upwelling. It would be pushing the crust of the Earth upward, forming a mountain. Okay? And also, one of the consequences would be reverse and thrust faulting. Volumetric strain under compression is given by the change of volume in relation to the original volume. So the volume shift here, volume shift rate. Epsilon V is given by delta V divided by V. As further explanation on the folding and reverse and thrust faulting, the first two. So for the folding, you have a plate pushing against another plate. It would start folding like that, okay? So it would start rolling, so to speak, against the other plate, like a paper. Now, for reverse and thrust faulting, so you would have one plate moving against another plate that is beneath it. So that would be the reverse. So the one that used to be behind is now in front, okay? And it is at the bottom of the other. So this one would go above it and like get over it, so to speak. It would cross it and becomes on top of it. That would be the reverse. Thrust would be more gentle, so to speak. So it would be like this plate here moving upward, being thrusted in the air. That would also, like, that would be the part that would form ridges and mountains. Okay, not mountains, but a ridge. Mountain building, when two plates pushing against each other, start welling up along with the pressure coming from the mantle. So it would create a mountain. At times, if the mountain is so thin, that would create the volcanic activity, because the crust would erupt due to high pressure and would form volcanoes. Tensional stress pulls rocks apart, causing extension and thinning, just like the divergent boundary. So sigma t is greater than 0. Common geological outcomes: normal fault formation, rift valleys. Okay, that would be a valley-like rift between two plates. Crustal stretching, so the crust would stretch out and it can form also what? Like a ridge, okay? So linear strain is defined as epsilon is given by delta L, which is the change in length, divided by L, the original length. Shear stress results from forces acting parallel to a surface. So tensile stress is normal to the surface. It would be pulling or pushing. Compressive would be pushing. Tensile would be pulling against the earth. Shear stress is parallel. So shear stress results from forces acting parallel to a surface, producing sliding deformation. Just like when you're pushing against a stack of paper, like the upper paper would go further than the lower than the lower. It would be deformed like this. T is given by F, force applied parallelly to an object, divided by the area of deformation. Shear deformation, shear strain is given by gamma is equal to tan theta, approximately equal to theta, where theta is the angular distortion of the Earth, okay, small angle approximation. Shear stress dominates along transform faults, okay, the faults of transform and strike slip earthquakes. So basically, let me represent it like this. You have Earth here, so with the force being applied like this, it would be moving with a very small slight angle theta. That would be theta. Since it is very small, it is approximated with tan theta. So this would be gamma, okay, shear deformation strain. Okay, with T, the shear stress is given by F parallel divided by A, the area at which it is applied, okay? That would be the area here, okay? The area of the Earth from above, to which the force is being applied. Elastic deformation. Elastic deformation is reversible deformation, occurring when stress remains below the elastic limit without breaking it, okay? Breaking that limit. So the rocks would return to their original shape after stress removal, after the stress has been removed. We've talked about that before. Hooke's law describes elastic behavior by being sigma, which is the stress, is given by E multiplied by strain. E is the Young's modulus that has to do with the material that we're talking about, okay? It's like coefficient of elasticity. For shear deformation, tau is equal to gy. G is the shear modulus, just like you have the elastic Young modulus E. Okay, shear modulus multiplied by the shear strain. How much you have a deformation, or the tan theta. Tan theta is being, you know, how much distance you had displacement for, okay, divided by the height of the area that has been displaced. So I will explain it further. Elastic strain energy stored per unit volume is given by U is equal to 1/2 sigma epsilon. This stored energy is released during earthquakes. To give a better idea on gamma, the shear strain. So let's say you have this part of the earth and it had a force, shear force being applied to it. So it will be displaced like that, okay? That would be the degree of displacement, okay? Now, so what would be the angle of displacement? It would be like this angle here, okay? Yeah, this angle here. Theta. Gamma, which is the shear strain, is given by tan theta, which is the amount of displacement, x, divided by the height, correct? The height of this slab, y. Now, since the angle is so small, tan theta would be approximately equal to theta, to the angle itself. And g is the shear modulus, okay? Multiplied together, they would give us the shear deformation. Plastic deformation, and we've talked about that before. Plastic deformation occurs when stress exceeds the elastic limit. So the object can no longer recover its original shape and size, its original characteristics. It loses its elasticity, its resilience, and would permanently guard or conserve the new shape that it had gained. Okay? Now, in the case of rocks, it would break. Okay? That would be the breaking point. They can no longer retain their original form. So, you have this would cause a permanent deformation without immediate fracture. Not necessarily it would immediately fracture, but it would deform permanently, which means that even with the stress being released, they can no longer recover or restore the original shape and dimensional characteristics. Rock behavior depends on temperature, whether it's elastic or plastic. This is what we mean. Pressure being applied, strain rate, and rock composition or the structure within the rock. Okay? Plastic flow follows viscous rheology, which is sigma is equal to eta epsilon, where eta is the viscosity and epsilon is the strain rate. At greater depths, rocks deform plastically rather than fracturing, which explains why deep regions experience fewer brittle earthquakes. Why? Because due to high temperature, they deform and they become fluid-like. So they have a fluid-like aspect to them. That's why they deform much easily without breaking. So they don't break, they deform due to the high temperature, just like a metal being molten, okay, with applied heat, overheat, and with applied pressure, it deforms. It doesn't break. Where does it break? At lower temperature, it gets to a point where it no longer, can guard its elasticity, but it ruptures. And this is why at higher altitude, at longer distances from the core, you have the occurrence of earthquakes is more prevalent, in respect or in comparison to a lower depths of the earth. Fault formation. A fault is a fracture in Earth's crust along with displacement which has occurred due to accumulated stress exceeding rock strengths. So the rocks could no longer withstand that stress. It formed a fault. It's like a scar on the Earth's surface. Failure occurs according to more Coulomb failure criterion. Tau is given by C plus sigma n tan phi. T or tau is the shear stress at failure, is given by C, which is the cohesion of rocks, plus sigma n, normal stress, 90 degrees to the plate, multiplied by tan phi, which phi is the inertial friction angle. Types of faults correspond to stress regimes. You have normal faults, which is a tensional stress, okay, longitudinal stress. Reverse thrust faults, which are compressional stress. So these are stresses that push against the rock. It's not like a tensile extensional stress, but it is a compressive stress. And slip faults, which are the shear stress. When two plates are shearing, they are gritting against each other sideways. That would be a shear stress. Effective stress, considering pore fluid pressure, is given by sigma prime is equal to sigma n, the normal stress, minus Pf, where Pf is the pore fluid pressure, okay? It is the pressure of the fluid. Increased fluid pressure can promote fault slip. Elastic rebound theory. Elastic rebound explains how earthquakes occur through cyclic stress accumulation and sudden release. So you have a cyclic accumulation of stress due to the pressure between different tectonic plates or due to gritting or moving away between two tectonic plates, thinning the crust, which can cause an earthquake, this time by the upwelling pressure from the mantle against the crest, and can also result in volcanic eruptions. The process: you have tectonic forces slowly deform rocks elastically. So tectonic forces, they slowly deform the rocks elastically, which means that to a certain point, if the pressure is to be released, they can retain their original shape. Energy accumulates at the rocks as elastic strain. Stress exceeds frictional resistance. Okay, then sudden rupture occurs along a fault. Suddenly, the plates rupture. Okay, you would have a break of the plate at or along a fault, which is a zone or an area where you have a weak crust, a weak layer of the earth. Okay, now rocks rebound toward an unstressed configuration. So once this pressure is released, the rocks rebound, which means that they fall back toward an unstressed configuration after releasing the energy. So, like they kind of fall back to a setting where you have no stress because the stress has already been released after the breaking phenomena, the rupture. The seismic moment describing earthquake size is given by m0 equal mu ad, where mu is the shear modulus. I know that this formula has been repeated more than once, but it is better, to have it registered. You can memorize it well in such case. So mu is equal to shear modulus, which is the resistance of a material against deformation. This is the shear modulus. Times A, which is the rupture area, multiplied by D, or the average slip displacement. The average displacement of the Earth. Radiated seismic energy is approximately proportional to the stored elastic energy with some waste. So, the seismic energy E is directly proportional to the stored elastic potential energy, which is m0. Finally, stress and strain govern how rocks deform under tectonic forces. Elastic deformation stores energy. Plastic deformation accommodates long-term flow. And brittle failure produces faults. The brittle failures, like the breaking failures. When accumulated elastic strain exceeds rock strengths, it breaks. You have sudden slip occurrence according to elastic rebound theory, and the rocks would retain or will fall back to an unstressed condition, unstressed position. So this would cause earthquakes, but also it can release the pressure from that strain, from that motion between the two plates. And the release of the pressure is actually the consequence of it would be the earthquake generation. Rock mechanics therefore provides the physical foundation for understanding seismic processes. Module 5, Faults and Earthquake Sources. Introduction. Earthquakes originate from sudden slip along fractures in the Earth's crust known as faults. These are weak areas in the crust where you have a movement, a motion, and an activity of tectonic plates. These faults accommodate tectonic deformation accumulated through plate motion. The physical characteristics of faults, their geometry, and rupture dynamics determine earthquake size, energy being released, how much of energy, and ground motion characteristics. So what's happening underneath? Is there a slipping, side slipping? Is there a convergence, meaning that the two plates are pushing against each other, or is there a divergence where the two plates are moving against each other, forming a ridge? Types of faults. Fault classification depends on the relative motion of rock blocks and the dominant stress regime. You have 1. Normal faults. So normal faults occur under tensional stress, where the crust is being stretched and the hanging wall moves downward relative to the footwall. Okay, so you have sigma 1 is equal to vertical stress, and sigma 3 is equal to horizontal stress. Characteristics, this is common in rift zones where you would have like a valley being formed, for example, at the bottom of the ocean, and divergent plate boundaries where two plates are moving away from each other. It produces crustal thinning, so the crest would thin out and it would start sinking down. Typically, they would cause shallow earthquakes. So to give you a better picture, you would have two plates moving away from each other. So here, this crest would start thinning, okay? So the top crest would start falling to the bottom crest, okay? To like the bottom of this thin crest layer, okay? Where did it mention it? So the crust is being stretched, exactly. It is being stretched. As you stretch the crust, it is being stretched, it becomes like that. Because of the motion of the two plates. That is divergent. They are moving away from each other. Okay, so the hanging wall moves downward relative to the foot wall. That would be the hanging wall here. It moves downward toward the foot wall. That would be like the wall underneath at the bottom. All right, it produces crustal thinning again. Produces crustal thinning and usually produces typically shallow earthquakes. This is characterized by commonality in rift zones and divergent plate boundaries. Slip displacement produces extensional strain, which is given by the difference between the new length of the fault minus the old length, so how much displacement we got, divided by L, which is the original length. That would give you the strain. Reverse and thrust faults. Unlike the case of divergent boundary, where you have two plates moving away from each other or apart from each other, here what you have is reverse and thrust faults in the case of a convergent boundary that form under compressional stress when the two plates are pushing against each other, where the hanging wall, the upper wall, it would move upward relative to the foot wall, and we're gonna represent it in an illustration in a moment. When the fault angle is shallow, less than 45 degrees, the structure is called a thrust fault. Sigma 1 is the horizontal compression in this case. The characteristics, okay, are the following: occur at convergent plate boundaries, as we mentioned before, associated with mountain building, so they build up mountains, and capable of producing large earthquakes. So to give you a picture, let's say you have a convergent boundary where two plates are moving against each other. These are the two plates. Now, what will happen is that the upper wall, so you have, this is the layer, this is the upper wall of the layer, the crest layer, and this would be the bottom wall, okay, the lower wall. So upper wall, UW, and lower wall, LW. This upper wall would start pushing or going upward in respect to the bottom wall. So the upper wall, again, would start pushing upwards like that. What it means is that this kind of motion, which is the convergent boundary, is contributing to the creation of mountains. It is associated with mountain building. And when you have a break in that motion, it will release so much energy because it is compressive. It is building up much more pressure than the divergent boundary, where you have a thinning layer of the crest. Work done during compression relates to stress and strain energy. So U is given by 1/2 sigma epsilon, where sigma, of course, is the tensile stress and epsilon is the strain. Strike slip faults. Strike slip faults involve horizontal motion parallel to the fault plane caused by shear stress. So T is equal to F parallel divided by area. You have two types here: right lateral, which is dextro tension, and left lateral sinistro. These faults are typical of transform plate boundaries and generate shallow but destructive earthquakes. Fault geometry. It describes the orientation and spatial configuration of a fault. Key geometric parameters include strike, so that would be the direction of the intersection between the fault plane and the Earth's surface. So that would be the fault plane and the Earth's surface. That would be the intersection between the two. It's like a boundary. Dip, angle between the fault plane and horizontal. So the fault plane, let's say the fault plane is like, that is the tectonic plate here. That is the fault plane. And the horizontal plane, which is the surface of the Earth, so to speak. So that would be 45 degrees in such case. Okay? It is called the dip. And rake or slip angle, so direction of motion along the fault surface. Let's say this plate is moving against that. That would be the slip angle. And finally, again, going back to the strike, direction of the intersection between the fault plane and Earth's surface. Okay, the horizontal and the plane where the fault is taking place. Slip vector magnitude is given by d equal square root of dx square, which is the displacement on the x-axis, plus dy square plus dz square, where the x, dy, dz are displacement components. So the magnitude, the overall magnitude in 3D space would be the square root of the sum of the squares of each one of the components. Stress acting on an inclined fault plane can be resolved into normal and shear components by adding theta, which would be the angle, okay, the angle of inclination, so to speak. So sigma n is given by sigma cosine square theta, and tau is given by sigma sine theta cosine theta. That would be the tensile stress, where theta is the angle between stress direction and fault plane. So for instance, let's say you have here the inclined plane and the parallel plane, or the projection of this inclined plane to the horizon, and theta would be the angle between both. So cosine theta would be equal to, that would be sigma n, and that would be sigma. So it is sigma n over sigma. So sigma n should be equal to sigma cosine theta, except here you have a square cosine theta due to the fact that a second order derivative has been executed. That would be for the normal stress, by the way, the stress that is normal to the ground, 90 degrees to the plate rather, not the ground. Okay, 90 degree normal. Now for the shear stress is given by sigma sine theta cosine theta, where theta is the angle between the stress direction and the fault plane. So let's say the stress direction is like this and the fault plane is this one. That would be theta. Hypocenter versus epicenter. Hypocenter, the point within the Earth where the rupture initiates. That's inside the Earth, not on the crust level. That's on the inside of the Earth. It represents the origin of seismic waves, where the rupture had occurred, or the breaking of the plates, or the sliding, or whatever you want to call it, depending on the scenario. This is where the earthquake had originated. Now the epicenter is the point on Earth's surface directly above the hypocenter. That would be called the location of the earthquake when they talk about the GPS location. Now the distance to an earthquake is estimated using the arrival time differences between seismic waves, which are Ts, time of arrival of the S wave, minus Tp, which is time of the arrival of the P wave. Okay, so delta T is Ts minus Tp, This gives us the time of arrival from which we can derive the distance. Now, again, as a reminder, the P wave is the compressive extensive wave, okay? That is the type of wave that travels quickly within rocks, within gas, within liquids. But the S wave is the kind of wave that is a shear wave. It goes up and down, okay? It doesn't travel longitudinally, and it cannot travel through liquids or fluids in general, also in gas. The epicentral distance is approximated by the following formula. D is equal delta T divided by 1 over Vs, which is the speed of the S wave, minus 1 over Vp, or the speed of the P wave, where Vp and Vs are seismic wave velocities. Rupture propagation. Earthquake rupture spreads outward from the hypocenter along the fault plane. Rupture velocity Vr is typically a fraction of shear wave velocity. Vr is approximately 0.6 minus 0.9 Vs, which is the shear wave velocity, S wave. Slip occurs when shear stress exceeds frictional resistance. Okay, so when shear stress exceeds frictional resistance, this is when you get a slip of the crack, or like the fault line. T would be, in such case, the shear stress greater than or equal to mu f sigma n, where mu is the coefficient of friction for the material, the earthly material that we're addressing here, okay, which is that of the crest and the upper layer of the mantle, multiplied by sigma n, which is the normal stress. Energy release during rupture is divided into seismic radiation, fracture energy, and heat generation. So it also generates heat. The radiation energy relates to stress drop, or the differential of stress, okay, the drop of stress. So what the stress used to be, then what it has become, all of that would be converted into radiated energy, which is given by delta sigma is equal to 7 over 16 multiplied by m0, which is the moment, seismic moment, divided by r3, or the radius of the rupture, to the power of 3. Now, for another node, the radius is measured from the hypocenter all the way to the point where the slip has stopped. In case it hasn't been clarified, this is the radius of the rupture. Seismic moment concept, and we've already talked about that, but as a review, the seismic moment is the fundamental physical measure of earthquake size, independent of observational limitations. M0 is given by mu AD, M0 being the seismic moment in Newton per meter, is given by the shear modulus of rock, which is the rigidity or resistance against deformation, multiplied by A, the rupture area, times D, which is the average slip displacement, how much the earth had displaced. Moment magnitude, MW, is derived from seismic moment, M omega rather, is equal to 2/3 log base 10 m0 minus 6.07. That's the moment magnitude. It is a logarithmic scale reflecting exponential growth in released energy. Approximate radiated seismic energy relation is given by E is approximately equal to or proportional to 10 to the power of 1.5 MW, which is the moment magnitude, indicating that each unit increases in magnitude corresponds to roughly 32 times more energy release on a logarithmic scale. Finally, faults are the physical sources of earthquakes formed by tectonic stresses acting on brittle crustal rocks close to the surface, close to the crust, and within the thermosphere. Okay, fault type depends on stress regime, while geometry controls rupture mechanics and seismic radiation. Okay, earthquakes initiate at the hypocenter, which is within the earth, propagate dynamically along faults, and release energy quantified by the seismic moment, M0, providing the physical foundation for modern research in earthquakes and modern evaluation and calculation in magnitudes, such as the Richter scale. which is, by the way, the logarithmic scale. Module 6, seismic waves. Seismic waves are elastic waves generated by the sudden release of energy during an earthquake. These waves propagate through the Earth's interior and along its surface, carrying information about the structure, the inner structure of the Earth, the Earth's interior, and along its surface. It reveals like the geological structure of the different layers of the Earth on the inside. Seismic wave analysis forms the foundation of seismology and earthquake detection. Now, to emphasize on an important point here, how do seismic waves have the ability to reveal the geostructure, like the geological structure of the internal layers of the Earth? This is due to the fact that waves have their characteristics such as magnitude, such as direction, speed, and even resonant frequency. These different characteristics, these different parameters are altered and changed by different foundational substances within the Earth. Different layers of whether rocks, whether silicate, whether fluids, like that would be molten rocks, iron, nickel, different structures, different foundational structures within the Earth can change or alter the frequency, the velocity, and the amplitude, even by dampening or attenuating different waves traveling within the Earth, especially the P waves, because we know already that the S waves are blocked by liquids. They can no longer travel within liquids. So they are stopped by that kind of liquid. So by that blocking, you can understand where these waves are coming from within the Earth and where they would be blocked. Okay? And by differentiating between where the P waves had reflected the deepest point within the Earth from which they came back from, and where the S waves would no longer be reflected, this would give you the width of the core that is liquid, okay? That is liquefied. Seismic motion satisfies the elastic wave equation, which we've seen before, but we're gonna revisit it right now. So it is given by nabla square u is equal to 1 divided by v square, second derivative of u in term of time. U being the displacement vector, the second derivative, because the first one would give you the velocity of displacement, so the second would give you the acceleration, how fast the displacement had occurred. Or in calculus, that would be the concavity of the displacement curve. V being the wave velocity, okay, so 1 over v squared, and t being the time being measured, reference time. Body waves. Body waves travel through the interior volume of the Earth and are the first waves recorded by seismographs. P waves, primary waves. What are the P waves? Here we go deeper into the definition of a P wave. Now, P waves are compressional or longitudinal waves in which particle motion is parallel to the direction of propagation of the wave itself. The characteristics are the following: fastest in seismic waves or among seismic waves, so they are faster than the S wave. They can travel in liquid, solids, and gas alike. Of course, the frequency and the dampening would be different among these different geological areas, so to speak. And they are the first arrivals on seismograms. They are the first ones to be detected by a seismogram. Now, as we mentioned before, the wave velocity depends on elastic properties such as the bulk modulus K, the shear modulus, and density. Vp is given by the square root of K plus 4 divided by 3 mu, which is the shear modulus, divided by rho, or the density of the Earth in that area. Particle motion produces alternating compression, and that would be like lateral. It would be parallel, in the parallel direction, and dilation regions. So you would have compression region, but also next to it, a dilation region where the Earth would stretch. Also here, another note that we've picked up before, which is that in lower areas of the Earth, so deeper undergrounds, would have a higher velocity of traveling of these P waves. Why? This is due to the fact that you would have a higher bulk modulus because the Earth is more rigid, and bulk modulus represents a measurement of the rigidity or solidness, the stiffness of rocks within that area, and also higher shear modulus, which is the resistance of an Earth's material against deformation, against twisting or deformation in general. S waves or secondary waves. S waves are transverse waves where particle motion is perpendicular to wave propagation. So let's give you a representation. Let's say this is the wave. So the shear stress would be going like that, up and down against the ground. That would be the motion of the ground here. So they would have a 90-degree angle with the wave propagation. They are slower than P waves for the S waves. They cannot travel through liquids and gas, so they can only go through solids and cannot propagate through liquids, which we've just mentioned also. Now, the velocity is given by Vs equal square root of mu divided by rho. Since in the liquids, the shear modulus is equal to 0, in other words, there is no resistance whatsoever to deformation. Fluids deform so easily. Like they immediately lose their characteristics, their physical characteristics, because there is none. Their only physical characteristics or characteristic is defined by the bowl or like the container that's holding that fluid-like substance. That's why shear modulus is 0 and Vs would be 0. In other words, the S waves cannot travel in liquid substance. S waves vanish in liquid regions. They are immediately halted and stopped, providing evidence for Earth's liquid outer core. That would be the way in which they had discovered, the existence of a liquid core underneath the Earth. Why? Because the P waves had made it all the way through and got reflected. Meanwhile, the S waves were blocked by that area, so they never came back. Surface waves. Surface waves travel along Earth's surface and generally produce the strongest ground shaking, ground motion, and most structural damage against buildings and different man-made structures. The love waves, these are categories. So the love waves involves horizontal side-to-side motion, perpendicular to the propagation direction. So that would be, let's say, the propagation of the wave would be like this, going up and down. So that would be like this, the side-to-side motion, which is 90 degrees against the plane of the wave propagation in such case. Characteristics confined near Earth's surface, so it is near the crest, require layered media, layered carrier, which means, in other words, the upper layer, that would be the media, the carrier of the waves. That would be the crust, and cause strong horizontal shaking. Approximate love wave velocity satisfies VL is less than Vs. So the love wave velocity means the velocity of that kind of wave would be less than the S wave velocity, and depends on shear velocity contrast between layers. The wave motion can be expressed as Uy, that would be the displacement vector, xzt is equal to a to the power of, a exponential minus kz. K is the wave number, z is the z direction, a is the amplitude, times sine kx minus omega t. Omega is the pulsation or the angular frequency, which is omega equal 2 pi times frequency, and k is the wave number here again, x being the x displacement, the x-axis motion. Actually, to simplify it a little bit, any type of wave is given by, let's say, u is equal to amplitude times sine, that would be the one holding the frequency, sine meaning that it starts from 0 and it has a frequency, kx is the number of the wave, the first wave, second wave, third wave, etc., next to each other, minus omega t, which is 2 pi times f, the frequency of the wave, times t, which is t on the timeline. So for t is equal to 0, that would be sine kx, okay? So for k equal, let's say 1, that would be, actually k would be in such case 0, okay? So sine 0, 0, you would have no wave. And the amplitude in such case is 0. Then it starts growing. So for k, let's say it's equal to 1, and t is equal to whatever, okay? You would measure a sine value here, and that would be the amplitude, by the way, okay? So it's propagating. It has multiple numbers. Why? Because you have the first wave starting from the center, then the second, then the third, etc. Rayleigh waves. Rayleigh waves produce retrograde elliptical particle motion similar to ocean waves. Characteristics, they are vertical and horizontal, like their mobility is vertical and horizontal waves. Energy decreases exponentially with depth, so as depth increases, also the energy would deplete almost immediately, very fast. And often largest amplitude waves. They would have often largest amplitude waves. As we mentioned it before, the nature of these waves is rotational. And as you go deeper within the Earth, that energy depletes exponentially. Often, these types of waves have a larger amplitude, although the fact that they decrease immediately within depth, but they have a larger magnitude, a larger height, okay, which makes them even more dangerous on the surface of the Earth. The Rayleigh wave velocity is approximately VR, is directly proportional, by the way, to Vs, and is almost equal to 0.9 Vs, with Vs is the velocity of the S wave. Particle displacement components are given by Ux is equal to A exponential minus kz cosine kx omega t. Uz is equal to A exponential minus kz sine kx minus omega t, etc. Now, wave propagation principles. Seismic waves obey fundamental physical principles. First, you have the reflection and refraction, just like when we talk about ordinary waves in physics. Here, they obey the same concepts. They follow through the same physical laws. At material boundaries, waves follow Snell's law, which is sine theta divided by V1 would be equal to sine theta 2 divided by V2, where theta 1, theta 2 are equal to incident and refracted angles, and V1 and V2 are wave velocities in different media. So, to make it a little bit more simple, you would have a wave traveling like this here. That would be, let's say, the mantle as an example. This is the mantle. And here is the crest. So you would have here a refraction, okay? So you see the wave had formed a direction, like it had diverted from its original path. I'm not saying that this is accurate here, by the way, because the direction would change based on the index of refraction, okay? So let's say here that would be theta 1, and that would be theta 2. So V1, which is the velocity of the wave within the mantle, is V1, and V2 is the velocity of the wave within the crest, okay, outside of the mantle. So sine theta 1 divided by V1 is equal to sine theta 2 divided by V2. Now, if you can imagine that here the lower area would be water, it would have a higher index of refraction, like in comparison to the air which is above it. Okay, we're gonna consider that. The layer above the water is the air. Just like when you see a twig within water, looking from above, you would see the twig broken. This is due to the refraction index, okay? So the water has a higher refraction index than the air. So, which makes the light bend as it goes out from the pool, the water pool, and this is why it reaches your eye with an inclination, okay? and it would seem for you that the rod or whatever has been submerged is broken within the water, which is not the case. Okay, this is due to the same phenomena. The point here is to determine what kind of media the wave is traveling through based on the differential of velocities. So when the velocity changes, also this would indicate that you have a different material with a different index of refraction. Superposition. This is when you have multiple seismic waves combined linearly. They add up to each other, forming a larger wave with a more potent power. That would be U total is equal to sigma UI, producing interference patterns. Okay, so they interfere against each other, and that interference would magnify even the colliding waves, producing a more powerful effect, just like when you have an explosion contained with a small sealed area, okay, within like a sealed container, an airtight container. It would magnify the explosion. Why? Because that high pressure would contain like these different explosion waves, the different shock waves would keep colliding against each other, magnifying the effect of the explosion due to the interference factor. Energy conservation. Wave energy flux decreases as distance increases. So this is due to geometric spreading. As the waves spread, this is also will affect the potency and the magnitude of different waves, and the energy would be scattered and would be damped by different layers of the earth. So the energy being released is directly proportional to 1 over r squared, or to say it in a different way, it is inversely proportional to the distance from the hypocenter, the origin of the rupture. Okay, so this is for spherical wave propagation. As you go near the hypocenter, the radius would be close to zeros, so that would give you an infinite energy. Okay, in comparison to original value of the energies, that would be 1 over 0. Okay, because the radius would be 0. Now, as you go further from the hypocenter, that would increase the radius here, which is, by the way, the square value of the radius. So 1 over, let's say, 300, 400, 1000, that would indicate that the energy would be depleted after a certain distance from the hypocenter, and it would dampen and no longer be potent. Wave velocity and material properties. Seismic velocity depends on elastic stiffness and density. The general relationship is given by V is equal to square root of elastic stiffness given by the bulk modulus K plus 4 divided by 3 mu, which is the shear modulus. Both of them like defining the elasticity, okay, the rigidity and stiffness, and the resistance against deformation. For the shear modulus, bulk modulus defines the rigidity or the stiffness of a material. Okay, so by examining the velocity of the earthquake waves or the seismic waves, we can ascertain or estimate the rock structure or the earthly structure within that area, divided by rho, which is the density of the substance under the earth. Higher rigidity increases velocity, while higher density reduces velocity, reduces the same parameter. Elastic moduli relationships. K is equal to lambda plus 2 divided by 3 mu, where lambda and mu are Lamé's parameters. Okay, so the Poisson's ratio is given by nu equal 1/2 V square P minus 2V square S divided by VP square minus VS square, where VP and VS are respectively P wave velocity and S wave velocity. Through that measurement, we can be provided an insight into the rock composition and fluid content of the earth, where we're measuring that earthquake. Lambda, by the way, is a parameter related to incompressibility and volumetric change of rocks that are under pressure. So incompressibility and volumetric change ratio of the rocks or whatever substance that is under the pressure. Seismic attenuation. As seismic waves travel, amplitude decreases due to energy loss mechanisms, due to dampening being absorbed by different layers of the Earth. Geometrical spreading, amplitude decreases with distance, as given by this formula. AR is inversely proportional to the distance from the hypocenter, because as the wave travels, it starts dissipating, it starts attenuating, and we also have a phenomena called dispersion, where even the frequency itself would start like going down. So the wavelengths would widen, increasing the period and reducing the frequency of the original wave. Intrinsic absorption. Energy converts into heat due to internal friction. Attenuation follows an exponential decay. So A of x is equal to A0 exponential minus alpha x, A0 being the initial amplitude, alpha is the attenuation coefficient, and x is the distance. This is completely true, by the way, an interesting formula where you have relationship of attenuation, so how much does the amplitude deplete, or how much does it die out, in which respect. So that would be the relationship. It has an exponential decay, okay, given by A0, which is the original amplitude, exponential of minus alpha x, where alpha is the attenuation coefficient and x is the distance from the source, the rupture source or the hypocenter. Quality factor Q. Seismic attenuation is quantified by the quality factor. So Q is given by 2 pi multiplied by stored energy divided by energy lost per cycle. Amplitude decay with time is given by AT equal A0 E. If you remember, it was minus alpha x. So here we're going to replace alpha x with omega t divided by 2q, with omega being the pulsation, I believe. T is the time factor divided by 2q, which is q is seismic attenuation quality factor. Okay, quality factor given by 2 pi multiplied by the stored energy divided by energy lost per cycle. Okay, per each cycle of the wave. Low Q values indicate strong attenuation. Finally, seismic waves transmit earthquake energy through Earth's interior and across its surface. Body waves, P and S, reveal internal structure, while surface waves, the Love and Rayleigh waves, dominate ground shaking. So these occur over the ground. Wave propagation depends on elastic properties, density of the material or the rocks, and boundary interactions, how different boundaries interact with each other. Attenuation processes reduce wave amplitude exponentially with distance, shaping observed seismic signals and enabling interpretation of Earth's internal geological property or physical properties. Module 7, Measuring Earthquakes. Quantifying earthquakes requires accurate measurement of ground motion and energy release. Modern seismology relies on sensitive instruments, mathematical analysis of seismic signals, and standardized magnitude and intensity scales, basically logarithmic scales like Richter. Earthquake measurement allows scientists to determine location, size, source properties, and potential hazards. Seismometers and seismographs. A seismometer is an instrument that detects ground motion, while a seismograph records and stores the measured signal. The basic principle of that is that seismometers operate using the principle of inertia. So you have a suspended mass, like a pendulum, that tends to remain stationary while the ground moves, and as it moves, it will move with it a rolling tape, where the stationary inertic mass would hold a pen recording the motion of that paper, rolling paper underneath it, and this is how it records the magnitude and the frequency of the earthquakes, okay, while the ground moves beneath it. The motion of a seismometer can be modeled as a damped harmonic oscillator with a differential equation, actually, given by mx second, which is the second derivative of x, plus cx prime, first derivative of x, plus kx is equal to minus m U second derivative gt, which is the displacement. So UGT alone is the displacement, but with a second derivative, it becomes the ground acceleration. X is the relative displacement, K is the spring constant, okay, just like a spring motion. C is the damping coefficient here, and M is the mass. The natural frequency is given by omega n is equal to square root of K divided by M, where M is the mass and K is the spring coefficient, okay? The elastic coefficient, so to speak, of the spring-like material that is vibrating. Omega, by the way, is omega equal to pi f, which is the pulsation that gives you the frequency. Damping ratio is given by C, which is, the constant divided by 2 square root of Km, which K is the elastic constant, elastic coefficient, multiplied by M, which is the mass. Modern digital seismometers record displacement, velocity, or acceleration. And C is the damping coefficient here. Seismic recording principles. Seismic recordings, called seismograms, display ground motion as a function of time. Key recorded parameters are the amplitude, the frequency content, because as it moves, you have the frequency, how much it is like oscillating. How often is it oscillating in terms of time, which gives you the frequency. How many oscillations you have or cycles in 1 second. That's the frequency, by the way. And arrival times of seismic phases, which are the P wave and the S waves, respectively. The ground motion relationships are given by Vt equal du over dt. So the velocity of the ground is given by the derivative, first derivative of displacement in terms of time. And A of t is the second derivative of displacement in terms of time. In other words, that would be the acceleration. So it is the derivative of the velocity, the first derivative of the velocity, or the second derivative of the displacement. Epicentral distance can be estimated using arrival time differences between the S wave and the P wave. So delta t is equal to Ts minus Tp, because S arrives later than P. So this would give you a positive value, Ts minus Tp, divided by the inverse of the velocities of S and P waves, respectively. 1 over Vs minus 1 over Vp. Triangulation using multiple stations of measurement can determine the earthquake location, because one alone would only determine a distance, which would be a radius around the measurement location. In order to determine the exact location, you need to triangulate, meaning to use at least 3 stations in order to get the point where these different distances meet, where these 3 circles intersect. Magnitude scales. Magnitude measures the energy released by an earthquake and is logarithmic in nature. You have the Richter magnitude, ml. The Richter scale was originally developed for local earthquakes using maximum wave amplitude recorded on a standard seismograph. ml is given by log base 10 of A, which is the measured amplitude, minus log base 10 of A0 delta, which is distance correction factor. Delta being the epicentral distance. Now, the epicentral distance, by the way, is actually determined using the previous formula, which is the difference of time divided by the inverse of S wave velocity and P wave velocity. Difference of time is actually the temporal distance between the arrival of the P wave and the S wave. The S wave, by the way, to be noted that it arrives later than the P. So difference of time divided by 1 over Vs minus 1 over Vp gives you the distance, from which we can derive the shift or the correction factor of the amplitude, because the amplitude that is detected is actually attenuated from, so it is lesser than the original amplitude A0 at the hypocenter. Properties, logarithmic scale. Increase of 1 unit corresponds to 10 times amplitude increase. Energy increases by approximately 32 times because it is logarithmic. Energy magnitude relationship is given by E is directly proportional to 10 to the power of 1.5 m. Moment magnitude, and we've seen that also before. So the moment magnitude scale is now the standard because it is physically based and valid for all earthquake sizes. You have the seismic moment. M0 is equal to mu AD. Mu is the shear modulus, A is the rupture area, and D is the average slip or displacement. Moment magnitude is defined as MW equal to 2/3 log base 10 of M0, which is the seismic moment, minus 6.07. Advantages: does not saturate for large earthquakes. So you have a logarithmic scale that is resilient, like for both. It is adaptive for both very low values and very high values because it increases like slowly, gradually, and it can even encompass larger values. And it is directly related to fault physics. Earthquake intensity, modified Mercalli scale. Unlike magnitude, intensity measures observed earthquake effects at specific locations. You have the modified Mercalli intensity MMI scale ranges from 1 to 12. I is not felt. So when we talk about degrees, 5 felt by most people, 7 or 8 severe damage, and 12 would mean total destruction. That would be of a stellar scale, so to speak. Intensity depends on distance from epicenter, local geology, which means like the internal structure of the earth at that location, building like beneath the ground where you are measuring the intensity of the earthquake, building construction, which means what do you have as a structure, what are the types of the buildings, do you have skyscrapers, have you implemented any protection against earthquakes within these buildings, okay, as a civil engineer, so to speak. Ground acceleration relates to perceived intensity in such case, so I is directly proportional to log base 10 A max, where A max is peak ground acceleration. Seismic data interpretation. Data analysis extracts earthquake properties from recorded signals. So you have the earthquake location, as we mentioned before, using travel time curves. It is given by distance divided by velocity. This is the formula, okay? So you have time curves. From T, you can get the D, the distance from the central location, from the epicenter. Okay, multiple stations allow triangulation of hypocenter position also. Frequency analysis. Seismic signals are decomposed using Fourier transforms that stipulates that any type of signal can actually be decomposed into a sum of sinusoidal signals. This is the theory. So U omega here in the Fourier transform, we transform this signal from the time domain into a frequency domain to extract the harmonics or different frequencies that are underlying within the signal with their respective amplitudes, of course. So U omega is given by integral from minus infinity to plus infinity, or sum of ut, which is different time signals, time domain signals, multiplied by exponential of minus omega t dt. Now the frequency content helps identify the following. The source characteristics, which has to do with different harmonics or different frequencies, because you would have different resonant frequencies as the signal travels through multiple layers of rocks. More than that, the velocity would change of different frequencies. That's one. Second, rupture duration. So when you have, for example, narrow frequencies that are short, okay, and narrow frequency signals like peaks, this indicates a shorter rupture duration. So the rupture had a high frequency. In other words, it occurred very fast. Plus site amplification, which means how much the site itself and the content of rocks, like different geological structures, had magnified the original signal at the hypocenter. Source parameters, the stress drop estimation would give us the distance to the source. So delta sigma, which is the drop of the tensile stress, is approximately 7 divided by 16 m0, which is the seismic moment, divided by r to the power of 3, which is the rupture radius. For magnitude and energy estimation, radiated energy relates exponentially to magnitude, given by E equal E0 times 10 to the power of 1.5 m, which is the magnitude, where E0 is the reference energy constant. Finally, earthquake measurement combines instrumentation, signal processing, and physical modeling. Seismometers record ground motion, seismograms reveal wave arrivals, and magnitude scales quantify energy release. The Richter scale measures wave amplitude, while moment magnitude relates directly to fault mechanics. Intensity scales describe human and structural impacts, and seismic data interpretation enables accurate determination of earthquake source characteristics and hazards. Module 8, Earthquake Location and Analysis. Determining where and how an earthquake occurs is one of the central goals of seismology. Earthquake location and analysis rely on seismic wave arrival times between P and S, mathematical modeling, and inversion techniques to estimate the hypocenter, rupture characteristics, and post-seismic behavior. Accurate earthquake analysis is essential for hazard assessment and understanding tectonic processes. Triangulation methods, which means measuring the distance to the epicenter from multiple, actually at least 3 seismographic centers in order to identify exactly the location of the epicenter of that earthquake. So earthquake location is primarily determined using triangulation, which combines seismic observations from multiple stations. Each seismic station measures the arrival times of P waves and S waves to determine the distance to the center of the earthquake. But the distance alone cannot isolate or locate the exact position of the earthquake, the exact fingerprint on the Earth's global circumference. Okay, so difference in arrival times provides the distance from the station to the earthquake, given by delta T is equal to Ts minus Tp. Using known seismic velocities, the distance to the source is given by D equal delta T, which is the differential of time between S and P wave, divided by 1 over Vs minus 1 over Vp. D is the distance to the earthquake, and Vp, Vs are velocities of P and S waves, respectively. To give you an exact approach, so here, let's say the distance has been given by D from the seismographic center to the earthquake. This alone would mean that you have a potential earthquake or epicenter is around that circumference, around the circle, okay, on the circle around the center, which is where we measured. Okay, so when you're measuring from 2 locations, so that could be here or here. So you can get 2 locations, possible locations of the seismographic activity, okay, when you have 2 seismograms. But when you have 3, this would triangulate at 1 location, okay? So let's say you have the third center here, so the center of location or the epicenter of the earthquake would be exactly triangulated or defined precisely. So to make it a little bit clearer, that would be the first, that would be the second, or that would be the second, intersecting in 2 points, and the third would be like this. So you would locate exactly the point of the earthquake, which is the epicenter. Each station defines a circle of radius d centered at the station location. The intersection of at least 3 circles determines the epicenter. Mathematically, for station coordinates xy and y, xi, yi, okay, so the equation of the circle is given by x minus xy squared plus y minus yi squared These are the coordinates of the center of the circle, which would be the coordinate like of the center of seismology, okay, the measurement or detection center, is equal to di square, that is the radius of the circle, or the distance from the detection center all the way to the epicenter. That is di square, okay? This is, again, the equation of a circle with xi, yi being the latitude and longitude or the coordinates of the center of that circle. Solving simultaneous equations yields epicentral coordinates x and y. Travel time curves. Travel time curves describe how seismic wave arrival time varies with distance from the source. General travel time relation is given by T equal integral ds over vs, where ds is the path element, okay, the distance being traveled, divided by vs, which is the velocity along the path. Now, as you notice here, we have an integration. This is due to the fact that the time is not a linear value. It is actually an integral of different distances traveled in terms of velocity, okay? So you have ds over vs, so different distances traveled related to their different velocities due to the fact that the sound or like the seismic wave is traveling in unique, distinctive geostructural locations or areas within the Earth. So you have different geostructural areas, different types of soil, sedimentation, and rocks. So different types of velocities in each segment, in each path being traveled. In other words, you have different media. So you have the rock, you have like liquid areas, you have part of half liquid, half solid, iron, different metals. So you need to integrate the different times of traveling and their respective velocities in order to get the time. Because seismic velocity increases with depth, waves refract according to Snell's law, given by sine theta divided by v is equal to a constant value. Travel time curves allow identification of seismic phases. So we have direct waves, refracted waves, and reflected waves. Okay, so reflected being, the waves that reflect in other parts of the Earth and go back as an echo. Refracted waves would be something like that. So you'd have between different medias. Let's say here you have rock. Here you have a layer which is more of a soil-like layer. So different refraction indices would mean that, let's say here is the wave that's traveling. It would refract, meaning it would change direction. So this is the angle of incidence, alpha 1, and here alpha 2, which is the refracted angle. So sine alpha 1 divided by v1, which is the velocity within the first media, the rock-like media, is equal to sine alpha 2, which is the angle of refraction after crossing into the soil area, divided by v2, or the velocity of traveling waves within the soil. These curves are fundamental for locating earthquakes and determining Earth's internal structure. Determining epicenter and depth. Epicenter determination. The epicenter is the surface projection of the hypocenter. So it is the point right above the hypocenter, which is on the same line going from the surface of the Earth all the way to the center of the core. Okay, this is the path on which the epicenter exists, but it is the location right above the hypocenter where the rupture had originated. Okay, so it is exactly on the crust, on top of the Earth. You can measure it by using the latitude and longitude, so to speak. It is determined using triangulation from multiple stations. Residual error between observed and calculated arrival times is minimized. Delta Ti is equal to Ti observed minus T calculated. The optimal location minimizes the misfit function given by phi equals sigma delta Ti squared. Depth determination. Earthquake depth influences arrival times and wave amplitudes. Depth estimation uses arrival time differences of depth phases. That would be the P wave and S waves arrival times, and the waveform modeling. Travel time difference between direct and reflected phases is given by delta t equal to h, which is the focal depth, multiplied by cosine theta, which is the incident angle, divided by Vp, which is the velocity of the P wave. Seismic inversion techniques. Okay, seismic inversion estimates Earth's structure or earthquake source parameters from observed seismic data. Okay, so you go backwards, so to speak. The general inverse problem is d equal gm, where d is the observed data vector, is equal to g forward modeling operator multiplied by the model parameters. The solution minimizes data misfit by minimum between d minus gm square. That is the modulus between these two. Least squares solution, so m is equal to g to the power of t, g to the power minus 1, gtd. Applications include hypocenter determination, fault orientation estimation, velocity structure imaging, and tomographic reconstruction. So in a typical scenario, m would be the unknown velocities of different waves traveling. D would be the travel time of the waves, and by that, and here you multiply G, which is like a vector, a tensor, with its transpose. By that, and it is inverted, so by that reverse action, we estimate the compositional structure of rocks within the Earth where the waves had traveled. Aftershock analysis. Aftershocks are smaller earthquakes occurring after the main shock takes place as the crust adjusts to stress redistribution. Okay, so Omori's law, aftershock frequency decays with time. That's given by nt, which is the aftershock rate, is equal to k, empirical constant, divided by c plus t. T is the time of the main shock, to the power of p, also an empirical constant that is approximately equal to 1. The Gutenberg-Richter relation, magnitude frequency relationship, is given by log base 10, n, with n being the number of earthquakes with magnitude greater than or equal to m, is equal to a minus b m, where a and b are constants. B value provides insight into the stress conditions. Stress transfer. So the stress change following rupture influences aftershock distribution. Okay, the relationship is given by delta t, which is this change in stress, okay, delta tau rather, is equal to the shear stress change, delta sigma, before and after the rupture, plus mu prime, delta sigma n. Mu prime is the effective friction coefficient, and sigma n delta is the normal stress change, normal being 90 degrees. Okay, sigma is the shear stress, that's parallel. Positive stress change promotes further earthquakes. Finally, earthquake location and analysis integrate observational data with mathematical modeling. Triangulation and travel time curves determine epicenter and depths, while inversion techniques extract physical source properties. Aftershock analysis reveals stress redistribution after the break, after the rupture, and seismic hazard evolution. Together, these methods form the analytical core of modern seismology. Module 9, Earthquake Energy and Ground Motion. Energy released during earthquakes. Earthquakes occur due to the sudden release of elastic strain energy accumulated in rocks along faults. According to the elastic rebound theory, first proposed after the 1906 San Francisco earthquake, tectonic stress builds up until failure occurs. That is the breaking within one of the plates, releasing stored elastic energy, which is a form of a potential energy that becomes a seismic energy, seismic waves. Seismic moment, which is m0, we've seen that before. The fundamental physical measure of earthquake size is the moment, given by mu ad, where mu is the shear modulus of rocks in Pascal, a the rupture area in meters squared, and d is the average slip, the average displacement. The moment magnitude scale is given by E approximately equal to 10 to the power of 1.5 mW moment magnitude plus 4.8. That's the energy is equal to 10 to the power of 1.5 mW plus 4.8 in joule. Energy increases exponentially with magnitude. An increase of 1 magnitude unit corresponds to approximately 32 times more energy release. Ground acceleration and velocity. The ground motion during earthquakes is described by displacement ut, velocity vt, and acceleration at. Vt is equal to the derivative of displacement over time. Acceleration is the second derivative of that displacement. PGA, or peak ground acceleration, is the maximum absolute acceleration recorded given by max A of t. It is commonly expressed in terms of gravitational acceleration g, with g equal 9.81 meter per second square. Peak ground velocity PGV is given by max Vt, so PGV often correlates better with structural damage than PGA. Wave propagation, and we've seen that before, for the P wave is given by square root of k plus 4 divided by 3 mu over rho. K is the bulk modulus, which is the rigidity or stiffness of a rock formation. Mu is the shear modulus, which defines the resistance of a material against deformation, divided by rho being the density, Vs being square root of mu divided by rho, and for liquids, mu is equal to 0. That's why S waves cannot travel within liquids or gas. Frequency content of shaking. Earthquake ground motion contains a broad spectrum of frequencies. The frequency content influences structural response. So by studying that content, we can assess the structural foundation, or like the geostructural of the underlying type of the underlying rocks, underlying layers of the earth. Okay, the structural geological substance, so to speak. Fourier representation. Okay, ground motion can be represented using Fourier transform, which, by the way, transforms from the time domain to a frequency domain, a type of signal. So you have a signal carrying different frequencies, but it is represented in the time domain. The Fourier transform, it translates, or like it moves that signal, the form of that signal, from the time domain into the frequency domain, where we can get different underlying harmonics, underlying frequencies with their respective amplitudes. This is what it actually does. U omega is given by integral from minus infinity to plus infinity, ut exponential of minus I omega t dt, where omega is the pulsation or angular frequency. Now, by analyzing the frequencies, the amplitudes, like the different harmonics, we can assess, first of all, for example, by observing the depression, the stress depression, or the stress change, you can understand the formation of the rocks, like the structure. When we examine different frequencies and whether they are short or long, like the frequency periods, and how repetitive they are, and the distance, the closeness of distance between different harmonics, and whether they are narrow or not, we can assess the rupture distance, which is the rupture period. How long did it take for the plate to rupture? And finally, you can get the distance from the hypocenter also by analyzing these parameters. Corner frequency. In the Brun-Source model, Fc, which is the corner frequency, is proportional to beta over r, where beta is the shear wave velocity divided by r, which is the source radius. This is a parameter from which we can get like the shear, or like the stress depression, or the difference of stress that can give you, by the way, like larger earthquakes have lower corner frequencies, longer periods of shaking. Spectral acceleration. Response spectra describe maximum acceleration for oscillators of natural period t, given by SA, t epsilon, not epsilon, key, is equal to max A, which is the acceleration oscillation function, okay, where key is the damping ratio. Site amplification effects. Local soil conditions significantly modify shaking intensity by amplifying the signal of like the seismic wave. Impedance contrast, and impedance being the resistance against the wave traveling within a soil. Wave amplification occurs when seismic waves pass from stiff bedrock to softer soil, where the shaking would become amplified. Amplification factor depends on impedance contrast, with Z impedance is equal to rho Vs. So it is equal to density multiplied by the speed of traveling. Reflection. Transmission coefficient at an interface is given by, so the reflection of the wave against an interface is equal to Z2 minus Z1. Z2 is the new media's impedance minus the first media impedance. Okay, so crossing from, let's say, from a magma field to a bedrock, okay, to a solid rock. Z2 would be the solid, that of the solid rock, which is a function of rho, density of the rock, times Vs, the velocity of traveling within that rock, okay, minus Z1. So Z1 being the one within the magma, although like the speed of S wave is halted within the magma. So we're talking about, it would be rather a form, another solid, a form of another solid structure, divided by Z2 plus Z1, which is the sum of the impedances between the bedrock and a softer soil, so to speak. Lower shear wave velocity soils amplify ground motion. So to give a better impression, let's say you have a solid rock here with a lower density, so rho here is lower, which means that Z would be also lower. This would be Z1. And soil above it with a higher density, so rho would be greater, and Z2 also would be greater, because Z2, the impedance, is a function of the density. So R, which is the reflection of the wave, is given by Z2 minus Z1, Z2 of the soil minus Z1 divided by Z2 plus Z1. This would give you the reflection ratio or reflection coefficient of the wave. By the way, the same concept is used in telecommunications. So the lower shear wave velocity soils amplify ground motion. Shear wave resonance in soil layers, fundamental side period is given by Ts equal 4h divided by Vs. H is the thickness of soil layer, and Vs is the shear wave velocity in soil, or the velocity of S wave within the soil. Okay, so 4h divided by Vs gives us the site period, the period of vibration, the vibration or wave motion period for that site. So for a thicker soil layer, you would have a longer period, okay? And like the contrary for the velocity, for a higher velocity, you would have a lower period of shaking, okay? You would have a lower site period. Resonance phenomena. Resonance occurs when the dominant frequency of ground motion matches the natural frequency of shaking or vibrating of a structure, such as a building, such as a monument, etc. So when these two frequencies, which is the frequency of the ground motion, matches the frequency of a building, you would get to a resonant frequency, like a tuning fork phenomena, which will endanger the building itself. Okay, it would get the building to start rupture, to start cracking, and it may collapse if that frequency persists. Natural frequency of a single degree of freedom system is given by Fn equal to 1 divided by 2 pi square root of k divided by m, where k is the stiffness and m is the mass. Now the period would be the inverse of that frequency, which is given by 2 pi square root of m divided by K. Equation of motion for a spring, which applies here in a damp oscillator subjected to ground acceleration, UGT, like an earth being shaken, it's given by mu second, which is the second derivative of u, or the acceleration of displacement, multiplied by m, which is the mass, plus cu, first derivative, which is the velocity of displacement, c being the damping coefficient, plus ku, which is the elasticity constant. Okay, elasticity coefficient multiplied by the displacement is given by minus m ugt. Second, which is the acceleration of displacement multiplied by the mass. Maximum response occurs when frequency of the ground is approximately equal to the frequency of the building, okay, the natural frequency. Finally, earthquake energy released is governed by seismic moment and magnitude scaling. Ground motion characteristics such as acceleration, velocity, and frequency content determine structural response. Local geological conditions amplify shaking through impedance differential or impedance contrast between like a rigid soil or rigid rock and soft soil, and resonance effects. When structural natural frequencies align with ground motion frequencies, this would lead to a resonant frequency. Resonance in such case can dramatically increase damage potential and collapse or the rupture of buildings, okay, and the breaking of different civil structures such as bridges and other monumental objects. Module 10, earthquake hazards. Ground shaking. Ground shaking is the most widespread and destructive earthquake hazard. It results from the propagation of seismic waves, P, S, and surface waves such as the love wave and the Rayleigh waves, generated by sudden fault rupture within the ground. Ground motion parameters. Ground motion is described by displacement ut and vt, which is for the velocity, and acceleration at, with vt is equal to the first derivative of displacement in terms of time or in respect of time, and at is the second derivative of displacement, d squared ut over dt squared. Key engineering parameters include the PGA, peak ground acceleration, which is the maximum value of at function, and PGV or peak ground velocity, which is equal to the maximum vt, velocity function value. Attenuation with distance. Ground motion amplitude decreases with distance due to geometric spreading and energy dissipation. This is equal to AR. Actually, it is inversely proportional to R, which is the radius, okay, distance from the hypocenter, times exponential of minus alpha r, with r distance from the source, again, n is the geometric spreading factor, and alpha is the attenuation coefficient of the wave that has to do with the material that the wave is traveling or traveling through. Empirical ground motion prediction equations, GMPEs, relate shaking intensity to magnitude, distance, and site conditions. Intensity scales. Shaking intensity is often described using the modified Mercalli intensity MMI scale, while magnitude, e.g. MW, quantifies total energy release. Surface rupture. So the surface rupture occurs when fault displacement reaches the Earth's surface. It is common in large, shallow earthquakes such as those along the San Andreas fault. Okay? Fault displacement. Average displacement relates to seismic moment. We've seen that formula multiple times already. So M0 is equal to mu AD. Mu is the shear modulus, the resistance of a material against deformation, multiplied by rupture area, multiplied by the average slip, okay, the slip distance. Surface offsets may reach several meters in large earthquakes, damaging buildings, roads, pipelines, and other infrastructure directly above the fault trace. That would be, by the way, the slip, okay, how much distance we have from or between the slipped ground and the original ground level, whether laterally or vertically. Liquefaction. This phenomena occurs when saturated, unconsolidated soils temporarily lose strength during shaking, so they lose their solid characteristics, becoming like a liquid state substance, okay, behaving like a fluid. It is common in loose sands and where you have a soft soil, okay, with high groundwater levels, especially when you have high groundwater levels, it mixes with the soil, so it leads to liquefaction, which means that this area, this thick layer of whatever, let's say soft soil or sand, becomes like a liquid state substance. It loses its firm or its solid, stiff characteristics. Effective stress principle. According to Terzaghis effective stress principle, sigma prime is given by sigma minus u, where sigma prime is the effective stress, sigma is the total stress, and u is the pore water pressure. During strong shaking, pore pressure increases, causing effective stress to approach zero. Okay, so sigma prime becomes zero. When sigma prime is approximately equal to zero, soil loses the shear strength. So it no longer acts like a solid state material. Okay, so the stress becomes equal to sigma prime, the shear strength becomes like, sigma prime times 10 phi, where phi is the inertial friction angle. So the soil basically starts acting like a fluid where the stress is no longer transmissible. Okay, it can no longer be transmitted as in the solid state type of soil or like structure. Okay, why? Because of like the pore water pressure acting or causing the entire soil, the entire structure, okay, causing it to act like a fluid, like water, for instance. So the stress is no longer with, like, it no longer has a potence to it. Hazards of liquefaction. Ground settlement, first of all, lateral spreading, sand boils, so the sand would boil up, like it would, you would have something like quicksands, foundation failure, failure of definite foundation. More than that, like the solid ground would no longer be as firm and it can no longer withstand the weight and the foundations of the buildings. Liquefaction caused significant damage during the 1964 Niigata earthquake in Japan, for instance. Landslides. Earthquake shaking can destabilize slopes, triggering landslides and rock falls. Slope stability is evaluated using the factor of safety Fs, which is equal to resisting forces divided by driving forces of the slide. So the failure occurs when Fs is less than or equal to 1, which means that the resisting forces are less or have become less than the driving forces. In other words, the soil or the rocks can no longer resist the driving forces, which leads to a landslide. In pseudostatic analysis, seismic acceleration is incorporated as a horizontal force. Fs is equal to Khw, where Kh is horizontal seismic coefficient and W is the weight of slope material. So you have the weight of slope material and Kh is the horizontal seismic coefficient. Earthquake-induced landslides were widespread during the 2008 Sichuan earthquake in China. Tsunamis. These are long wavelength sea waves generated by sudden vertical displacement of the seafloor. So whether, let's say you had a sudden upward motion between the tectonic plates, so they were pushing against each other and sudden it broke and like that ridge was suddenly elevated because adding to the peer pressure between the two tectonic plates, you had also the magma pressure from beneath. So it pushed upwards, causing the sudden motion of the waves and the release of energy. The seismic energy waves become are transmitted like they are transmitted as sea waves that get to the shore. Okay, commonly associated with mega thrust earthquakes and subduction zones. Also, you would have the case of a landslide within the sea floor or the ocean floor. So suddenly a land would depress downward, it would like sink suddenly and causing this kind of a oscillatory moment, oscillatory motion that would also generate waves manifesting as tsunami waves. Wave speed in deep water, tsunami velocity depends on water depth given by square root of gh, where g is the gravitational acceleration and h is the water depth. So, tsunamis can travel across ocean basins at speeds exceeding 700 kilometers per hour. This is how fast they can be. And again, this is the formula. So, C is equal to square root of gh. Wave amplification near shore. As depth decreases, wave speed decreases and wave height increases. Due to energy conservation, which means that the energy would still be conserved, however, it needs to be dissipated somewhere. Okay, that's the shoring effect, it is called. The devastating 2004 Indian Ocean tsunami followed a megathrust earthquake of Sumatra rather. Now, the increase of the amplitude as the tsunami wave gets in proximity with the shore is mainly due to the fact of two phenomena. One of them is the energy conservation, which means that the energy is still conserved. Plus, two is due to the fact that as the waves approach the shoreline, they are more compressed, which means that they get much closer to each other, increasing the amplitude height of each wave. So they become more severe. Due to the compression, they are no longer scattered, so the compression would pull the amplitude up. Okay, so they become higher at proximity with the shorelines. Secondary hazards. Earthquakes may trigger additional hazards, including fires like gas line ruptures, dam failures, hazardous material spills, such as fuel materials or other more hazardous materials, for example, radioactive materials, and infrastructural collapse, such as collapse of bridges, buildings, and finally, aftershocks. The aftershock frequency decay follows Omori's law, given by n of t is equal to k divided by c plus t to the power of p, where kcp are empirical constants, and n of t is the aftershock frequency. Aftershocks can significantly increase cumulative damage and risk following a major earthquake. Finally, earthquake hazards include primary effects such as ground shaking and surface rupture, and secondary effects such as liquefaction, landslides, and tsunamis. These hazards are governed by physical principles including wave propagation, effective stress, slope stability, and fluid dynamics. Understanding these mechanisms is essential for seismic hazard assessment, engineering design, and disaster risk reduction. Module 11, Engineering Seismology. Earthquake-resistant design principles. Engineering seismology applies earthquake physics to the design of structures capable of withstanding seismic loads. The fundamental objective is life safety, followed by damage control and functional recovery. Design philosophy. Modern seismic design follows these principles. Strengths: provide adequate lateral load capacity. Ductility: allow inelastic deformation without collapse. So, deformation that is not elastic, okay, that is like distorting the original shape of a building, but without a collapse, like using epoxy in the building material, in the cement, for example. Energy dissipation: absorb seismic energy through controlled yielding. Redundancy: providing multiple load paths so as to distribute the loads on the entire structure. And regularity: avoid geometric and stiffness irregularities. This last one is talking about avoiding having a weaker point within the building where load would dissipate and inflict damage. Okay, so we need a uniform structure where load can be distributed in different pylons, okay, without having a weak point that can break first and bring down the entire building afterwards. Equivalent static base shear, a simplified design force is given by V equal CSW, where V is equal to the base shear, W effective seismic weight, and CS is the seismic response coefficient. Typically, the seismic response coefficient is given by SAT divided by RI. So SAT is the spectral acceleration at period T, divided by R over I, which is the response modification factor, or ductility, over I, which is the importance factor. Structural response to seismic loads. Structures respond dynamically to ground motion. A building can often be approximated as a single degree of freedom, meaning that it moves only from above and it's fixed below. Okay? It is approximated as a piece of metal or an elastic rod that is moving only in one direction. Okay? Or SDOF, single degree of freedom. The equation of motion is given by, for the ground acceleration, mu is second plus cu prime plus ku is equal to minus mu second gt, where m is the mass, c is the damaging coefficient. By the way, here is the second derivative of u, which is the acceleration of displacement. U is the relative displacement, and u prime is the velocity of the displacement, which is the first derivative, with k being the stiffness or the elastic coefficient. Natural frequency and period. The pulsation, or the natural pulsation, which is equal to 2 pi times f, is given by square root of k divided by m. Okay? K is the elastic coefficient and m is the mass. Tn is the period, which is 2 pi divided by omega n. The damping ratio is given by C divided by 2 square root of Km. Okay, typical buildings have a value of damping ratio less or approximately 5% of critical damping. And again, C is the damping coefficient. Response spectrum. The maximum structural response is obtained from the response spectrum given by SAT. E is equal to max ut, second derivative, which is the acceleration of displacement. Response spectra from the basis of seismic design codes. Building resonance. Resonance occurs when the dominant frequency of ground motion matches or becomes very close to the building natural frequency. Actually, it should match. So F ground, when it is approximately equal to the natural frequency of the building, this is when resonance occurs and the building becomes like a tuning fork, with Fn is equal to 1 divided by 2 pi square root of k divided by m. Taller buildings would have larger mass, okay, and smaller k. So they have longer natural periods and are more vulnerable to long period ground motions, okay, because they would vibrate at lower frequencies. The amplitude magnification factor for a damped system is given by mw is equal to 1 divided by square root of 1 minus r square plus 2 k r square, where r is equal to omega divided by omega n. That's the maximum amplification occurs near r equal 1. And as a reminder, key here, this parameter is the damping ratio that we've seen in the other equation. So basically what we're trying to say is, when you have a longer building, let's say the lambda should match the longer building for it to tune. This is actually the case. So longer buildings would mean longer lambda, longer wavelengths, matching the tall, how tall the building is. So it would be longer period and lower frequency. So it would collapse and attain to the resonant frequency at a lower frequency of vibration. This is why it is critical. This is why it would be more vulnerable and dangerous. More than that, within the formula, you would have a larger m and a lower k, which is the elastic coefficient. That's why it would erupt even at lower frequencies. making it more vulnerable to earthquakes. Base isolation systems. Base isolation reduces seismic forces by decoupling the structure from ground motion. So in this way, you would have the ground motion kind of detached from the structural building itself. So the transmission of the vibration from the ground to the building would be damped by that technique. This technique was successfully implemented in buildings after lessons learned from events such as the 1994 Northridge earthquake in California. Okay, so this would protect the structure by, again, damping or removing the direct contact between the structure and the moving ground. Principle of isolation. Isolation increases structural period. So the period of isolation is given by 2 pi square root of m divided by k isolation, which is the coefficient of isolation, elastic coefficient of isolation. Since k isolated is much lesser than k fixed, okay, in this case, the period would be much larger, okay, than the period of a fixed building. This shifts the structure to a region of lower spectral acceleration. So it wouldn't accelerate as intensely, and thus it wouldn't attain the resonant frequency of the ground. Isolation force is given by F equal chi or K isolation multiplied by U, which is the displacement. Common systems include lead rubber bearings, so they would act like dampers or a system of a damper. Friction pendulum systems, okay, like pendulum at the base, okay, and they would damp the frequency of vibration with the building, so they would prevent the building from attaining the same frequency as the moving ground, thus eliminating the risk or mitigating the risk of having a collapse, okay, having a tuning fork effect. And elastometric bearings, which means that you would have within the foundational structure elastic material that would act as a damper, okay, that would reduce the frequency of the building. Energy dissipation is often enhanced by supplemental damping devices. Seismic building codes. Seismic codes translate seismological knowledge into enforceable design requirements. Examples include International Building Code, IBC, which is used in one software that I know. I won't mention right now its name, okay, but it is for simulation. Eurocode 8 and National Earthquake Hazards Reduction Program, or NEHRP provisions. Design ground motion. Code defines seismic hazard using probabilistic seismic hazard analysis, or PSHA. Okay, lambda IN greater than x is given by the second integral, which measures by the way, like the probability distribution in this case over a surface area, okay, of VMR, so, or new MR multiplied by PIM, okay, the MDR, where lambda is the annual exceedance rate, VMR or new MR is the occurrence rate of earthquakes of magnitude M at distance R. So it is a function of M and R. This second integral has, just like you would have the x dy to measure an area, here the second integral is in respect of M, which is the magnitude, and R, which is the radius. IM is equal to the intensity measure, and design spectra are typically based on a specified probability of exceedance, e.g. 10% in 50 years. Finally, engineering seismology integrates earthquake source physics, wave propagation, and structural dynamics to design earthquake-resistant structures. Structural response is governed by dynamic equilibrium equations, resonance effects, and damping. Base isolation and ductile detailing reduce seismic demand, while building codes ensure consistent safety demands or standards based on probabilistic hazard assessment. Module 12, Earthquake Prediction and Forecasting, Precursors and Warning Signs. Earthquake prediction seeks to identify reliable physical signals preceding the rupture Despite decades of research, no universally accepted short-term precursor has been established. The foreshocks. Some large earthquakes are preceded by smaller events, the smaller shocks, okay? They are called foreshocks. Seismicity rate changes may follow empirical laws such as the Gutenberg-Richter relationship given by log base 10 n is equal to A minus Bm, where n is the number of earthquakes with magnitude m greater than m or equal to, and AB are empirical constants. A deviation from background seismicity may indicate stress evolution. Strain accumulation. Tectonic strain accumulates at a rate epsilon is equal to V divided by L, where V is the relative plate velocity and L is the locked fault length. Geodetic monitoring, e.g. GPS, measures surface deformation to estimate the stress being built up. Other proposed precursors would be radon gas emissions that occur before the earthquake, the bigger earthquake. So they would be released from the earth and they act as an indicator that something is being ruptured underneath. Electromagnetic anomalies, so the change of the crest or the build-up of pressure within the earth would change or alter the electromagnetic field. So these anomalies would be a precursive indicator of an impending earthquake. Groundwater level changes also. You would have like a water receding to the ocean prior to a tsunami, for example. Seismic velocity, because you would have a landslide, then the water would be sucked in and the returning wave would hit back on the shore. Seismic velocity variations also. So a change in seismic activity, lower seismic activities. However, reproducibility and reliability remain limited. Okay, so they cannot be reproduced. Statistical forecasting. Unlike deterministic prediction, forecasting estimates earthquake probability over time. So you have the Poisson model. If earthquakes occur randomly in time, probability of n equal k is equal to lambda t to the power of k, exponential minus lambda t divided by k factorial, where lambda is the mean occurrence. This is, by the way, the Poisson rule. And lambda is the mean occurrence rate, t is the time interval, divided by the number of events factorial. Probability of at least one earthquake in time t is given by Pn greater than equal to 1 is equal to 1 minus exponential of minus lambda t. Time-dependent models. Renewable models incorporate stress accumulation and recurrence intervals. So Pt probability is given by 1 minus exponential of minus t over tau to the power of beta. Beta is the shape parameter and tau is the mean recurrence time. Of course, t would be the time being measured, okay, so the current time, so to speak. Aftershock forecasting. Aftershock rates follow Omori's law, given by n of t is equal to k divided by c plus t to the power of p. This allows short-term hazard updates after major earthquakes. Probabilistic seismic hazard assessment, PSHA. In another part, we've already seen that. So PSHA estimates the probability that ground motion exceeds a specified level at a site. Hazard integral is a secondary integral or double integral of nu mr PIM greater than x for m and r, and this is a function of both the magnitude and the radius. Okay? Lambda is being the annual exceedance rate that's being calculated. IM is intensity measure, okay, PGA spectral acceleration, that's the maximum acceleration, ground acceleration, and PIM is the conditional probability from ground motion models. Return period is given by TR equal 1 divided by lambda. Design levels are often expressed as a probability of exceedance, e.g. 10% in 50 years. Now, P probability of occurrence is equal to 1 minus exponential of minus lambda t. PSHA forms the scientific basis of modern seismic building codes. Again, lambda is the annual exceedance rate. Early warning systems. Earthquake early warnings, EEW systems, detect initial P waves. This is what they are about, and issue alerts before the strong S waves arrive. The warning time is given by if Vp and Vs are wave velocities, so delta T is equal to D, which is the distance, multiplied by 1 divided by Vs minus 1 divided by Vp, where D is the distance from hypocenter. Now, delta T is greater than 0, providing seconds to tens of seconds of warning, which is not much relevant, but it can be of some importance. Operational systems include Japan Meteorological Agency, JMA, EEW system, Shake Alert in the United States. Alerts can automatically stop trains, shut down gas lines for prevention, and open fire station doors. Limitations of prediction science. So, nonlinear fault dynamics. Earthquakes are governed by nonlinear frictional processes, given by tau equal sigma n mu delta theta, where theta or tau is the shear stress, is given by sigma n, which is the normal stress, 90-degree angle with the horizontal plane, okay, with the ground. Mu is the friction coefficient rate and state dependent, and delta is the slip rate. Small perturbations may trigger rupture, okay, reflecting chaotic behavior, so it's not necessarily linear, which makes it unpredictable. Uncertainty. Forecasts involve epistemic and aleatory uncertainty. Total uncertainty is often represented as sigma square total is equal to sigma square aleatory plus sigma square epistemic. Key challenges: incomplete knowledge of subsurface stress, limited historical records, complex fault interactions, okay, and difficulty distinguishing true precursors from noise signal. So the fault interactions also are complex. You have limited historical records, so you don't have a large database so as to make it predictable as you would want to, like inserting that into an artificial intelligence model that would be more accurate to predict the possibility or the high potential of an earthquake before it actually happens, and we don't have a complete knowledge of subsurface stress. Finally, earthquake prediction remains scientifically challenging due to complex fault mechanics and limited observable precursors. Statistical forecasting and probabilistic seismic hazard assessment provide practical tools for risk estimation. Early warning systems mitigate damage by exploiting wave speed differences, but precise short-term deterministic prediction is not currently achievable.